Welcome to the Curia Julia, and thank you for joining us in the afternoon session of the Bluenet meeting. Curia Julia is a building that was dedicated by Augustus in 29 before Christ, and it is Curia Senatus. I'm very happy to co-host this important meeting with the Accademia Nazionale dei Lincei. I wish to thank the organizer, Professor Antonio Sgamellotti. Grazie, thank you. And for involving us, and me in particular, in this interesting project on Egyptian blue. The subject is very dear to me, as I had started working on it years ago when I worked on the Etruscan tombs of Tarquinia. Tombs of Tarquinia. We're now undertaking researches on the subject also here in the archeological Parco of Colosseo, namely within the agreement between the Institute of Sciences of Cultural Heritage of the Sea and Air in Florence and the archeological Parco of the Colosseum. Shared research is being carried out. We are now analyzing materials and aspects related to the execution techniques of the fragmentary painted plaster from the 1950s excavation in the area of the House of Augustus on the Palatine, currently being studied by Roberta Alteri, Stella Falzone, and Silvia Fortunati. In the first campaign, the CNR researchers Donata Magrini, Emma Cantisani, and Silvia Bettori used non-invasive and portable analytical methodologies, carrying out the investigation directly on the fragments preserved on the park's deposits. Among the various research activities, archaeometric investigation, this is House of Augustus on the Palatine Hill. Among the various research activities, archaeometric investigation are being carried out to assess how the pigment known as Egyptian blue was used. I'm sorry. Okay. I'm sorry. I'm sorry. Okay, I'm sorry. Among the various research activities, archaeometric investigation are being carried out to assess how the pigment known as Egyptian blue was used. In fact, punctual analytical methods such as X-ray fluorescence, reflectance, Madonna, ma no, impossibile. I'm sorry. Okay. Dunque, reflectance spectroscopy and infrared spectroscopy were performed based on the result obtained from visible radiation-induced luminescence, which allowed the mapping of Egyptian blue. In particular, it was observed that in the analysis, the samples of painting the blue pigment is used in different ways, both pure as well as mixed with other pigments to obtain a wide variety of backgrounds from green to white or yellow tones. On a group of fragments belonging to a painting with an Egyptian motif, on a group of fragments belonging to a painting with an Egyptian motif, which can be assigned to the third Pompeian style, it's possible to observe how Egyptian blue is used everywhere below the painted figure. We can see. and thus was used as a mixture with other pigments. White, it is pure and in high concentration only in specific point, such as a palmette. The possibility of attributing the fragments found in the excavation in a secondary location to the known pictorial context to the Palatine is currently being assessed. The assessment is based also on the analysis of the painting technique and, more specifically, on the use of Egyptian blue in a mixture. A sampling of wall frescoes from the Roman period, still in situ in the archeological area of the park, will be the subject of a forthcoming survey campaign. Now, I wish you good work, and I give the floor to the chairperson. I don't know.
Thank you, Dr. Russo, for the wonderful hospitality. Dr. Russo was telling me before that this was the seat of the Senate during the time of Augustus. This room has been inaugurated almost 2,000 years ago. We get to use it today. Purple togas will be distributed later. It's my pleasure now to call to the podium Dr. Ariadne Kostomitsopoulou.
Yes. And how do I change the slides? So, good evening, everyone. Can you hear me? Yeah. So, it is today evident that Egyptian blue has been used continuously or almost continuously throughout antiquity and even until the Middle Ages, or in some cases later than that, across the Mediterranean world, and in many cases reaching further than that, the British Isles, or as far as Norway in the Roman period. As a pigment, Egyptian blue has found numerous applications, such as wall paintings, and we heard a lot of examples today, and we will continue hearing interesting examples also in the following talks. And of course, the discovery of Egyptian blue in Galatia's triumph, that was quite extraordinary and brought us all together today. Oh, it moved on its own. So the material's saturated blue color, combined with its compatibility with different media, led to its widespread use as a pigment, even though its properties as a vitreous material have also been exploited. However, despite the wide diffusion and use of Egyptian blue as a pigment for more than 4 millennia, evidence about the organization of its manufacture remain rather scarce. Throughout this it moves on its own, sorry. Okay. So throughout this presentation, Egyptian blue will be approached as an artifact, the final product of a series of technological processes, and not as a raw material, to be applied as a pigment. And this is quite important in the approach that I will be taking today. It helps us, if we see it as an artifact, to break down the procedure of pigment production by distinguishing the initial manufacture from further treatments. Such work, including mixing and grinding pigments, was to be performed by painters and their workshops. And this type of treatment must have reached a very high level of organization and standardization during the Roman period, and we heard a very nice overview of the wall paintings, the development of wall painting in Ostia today. But of course, these mixtures do create a more complex picture for provenance studies. So my focus will be the primary production, which would require a specialized workshop with permanent installations to materialize. In this search for these workshop spaces, I will try to bring together archaeological and scientific evidence and to compare the data with literary evidence. Finally, I will briefly present the archaeological evidence of Egyptian blue production on the island of Kos. Yes. Aiming to contextualize the production in a rather small and specific small-scale setting. Different names have been used from different culture across the material's rich history. And these names are often in association with lapis lazuli, the precious blue rock. The linguistic connections between the terms that have been considered by Hilary Becker in a recent article as indicative of trade networks with the East, with civilization of the Aegean with the East, and the import of raw materials, or of Egyptian blue and other blue materials from the East to the Aegean. However, the production of Egyptian blue might have had already spread across the Mediterranean world already from the Minoan period, and Anne Brisbard, in a publication of 2008, discusses this possibility based on the identification of tin in Minoan samples that predate the Egyptian blue samples with tin identified in Egypt. This train of thought, based on variations in the chemical composition of analyzed finds in specific chronological contexts, has formed hypotheses of local production centers in several occasions. We heard today the presentation about Eastern Anatolian production, and I have included the publication of the Ayanis fortress here, where the elemental analysis of the cakes or the ingots with this specific rectangular shape that we saw earlier today demonstrate a high zinc content and the absence of tin. And this is considered as a signature of local production linked to local metallurgical processes. However, to my knowledge at least, the exact location of the production site has not been yet identified. Indeed, archaeological evidence of production is scarce, and even in Egypt, the workshop remains of Egyptian blue production are hard to decipher. Early evidence of production has been unearthed at Amarna, where unused Egyptian blue has been found in workshop contexts, alongside Egyptian green, faience, and raw glass. Even though faience production has been thoroughly discussed by Nicholson, the archaeological remains of Egyptian blue production at Amarna have not been positively identified, the structures per se, most likely indicating that we have a smaller scale production compared to faience, or that the production of Egyptian blue was happening in parallel using the same structures as were used for faience production. After all, the ingredients required for the production of Egyptian blue overlap to a large extent with those for faience, so it would make sense to have this production running in parallel. However, here and in other cases that we will go through today, we encounter a series of problems that may impede our understanding of manufacturing sites or workshops. First of all, there is a problem of documentation, unfortunately, especially with earlier excavations, that is scarce or lost. And secondly, workshop remains themselves are particularly hard to decipher, to interpret, especially when more than one craft production was happening in the same place. Indeed, in several cases, what remains is the final product, either as an unused pigment or as an applied paint layer or an object. And the only information that we can extract comes from scientific analysis. Now, returning briefly to the archaeological evidence, Kantir Pirameses, excuse me if this is not the correct pronunciation, is another Egyptian site that is dated to the 13th century, with evidence of bronze casting and production of architectural faience. And there, the discovery of blue, Egyptian blue, in cakes and fragments of unused pigments in various qualities and in different stages of production have been linked to a local production again. Now going later into the Hellenistic and Roman period, the glass and faience workshops from Com Helul in Memphis have this large time span that I always find a bit difficult to grasp, but from the 3rd century BC to the 3rd century CE. And there, the famous saggars that are white-slipped and have Egyptian blue adhered in their interior surface have been unearthed. But again, the exact kilns that were used for the production of Egyptian blue are not easy to identify, even though the reconstruction of the faience kilns done by Nicholson might be like a very useful parallel to help us think how Egyptian blue was also fired. But there is a difference between faience and Egyptian blue, and this is that faience was meant to be produced as a final artifact, ready to be used. So there you had to be extremely careful not to ruin the color of what was going to be traded or exported. The evidence of Egyptian blue production in Egypt certainly justifies the contemporary term Egyptian blue, which in fact we can trace back to Theophrastus, who, writing in the 4th century BC, already states that the artificial pigment, kianos oskevastos, comes from Egypt. In the works of Vitruvius and Pliny the Elder, the sources of pigments, blue pigments, seem to increase or multiply, indicating on the one hand, a shift in the organization of the production, and on the other, possibly the newly acquired access to raw materials with the expansion of Rome, the Roman Empire. Vitruvius, writing in the 1st century BC, describes the establishment of a workshop in Puteoli, today Pozzuoli, by his contemporary man named Vestorius. And we are all very familiar, I think, with the much-discussed excerpt from the 7th book on architecture that discusses the process of Egyptian blue production at the workshop. Writing some years later, or a few decades later, Pliny the Elder includes 2 different varieties of Egyptian blue from that city, one named after the city, Puteolanum, and one named after the owner of the workshop. He also adds blue from Spain and different qualities of blue, but the blue from Spain, I should note here that is not quite certain if it's a mineral blue or if it's another production center for Egyptian blue outside of Italy. 19th century excavations at Pozzuoli, recently republished by Cavassa, have brought to light a storage space that is possibly related to the production of Egyptian blue. However, the remains of the workshop are yet to be identified. Whether Pliny's Vestorian and Puteolanian blue came from the same workshop, or if several workshops were established in the 1st century in Puteoli, remains unknown. What is indicated, however, from the archaeological evidence is that the Bay of Naples hosted workshop in at least 2 more towns, Literno and Cuma. This hypothesis is based on the discovery of saggars with Egyptian blue adhered on their surface and the discovery of technical ceramics, combined with the chemical analysis and the mineralogical analysis of both the Egyptian blue traces and the technical ceramics, suggests that sand deposits from the Bay of Naples could support a local production, and that the clay used for the production of the saggars was local. Now this, combined with the recent analysis on unused Egyptian blue samples from Switzerland from different sites, dated to the 1st and 2nd century, were identified as Egyptian blue from Naples, or from the Bay of Naples, based on their unreacted minerals that were identified by Raman spectroscopy in the finds, that match in composition with those from the Volturno sands. This, combined with the identification of the same minerals in a blue wall painting dated to the early medieval 5th or 6th century CE, again from Switzerland, is, according to the authors, a proof for the continuous production and monopolized trade of Egyptian blue from the Bay of Naples or the Phlegraean fields. However, the reality of the archaeological record seems to be a bit more complicated than just suggesting a standardized monopolized trade. And the late Hellenistic workshop, 1st century BC, let's say, discovered on the island of Kos, illuminates the multiplicity of production modes. Excavations carried out at the Ephorate of prehistoric and classical antiquities of the Dodecanese in the modern city of Kos, on the island of Kos, during the 80s, at an area that is identified as the eastern stoa of the Agora, brought to light the remains of a workshop that is dated to the late Hellenistic period. Yeah, I don't know if there is a pointer. Is there? Yeah, okay. At least 2 fire structures were identified at the site, one here and one here, most probably more, but in a very destroyed state. And in the westernmost fire structure, about 98 Egyptian blue pellets were found inside the pit, the fire pit. Moreover, burnt pine cones, pumice, a white substance that was identified as quartz by chemical analysis, carried out in the 80s, layers of sand, charcoal, dolomite, and also other pigments were found at the site. The other pigments, the so-called earth pigments, have been recently analyzed. Oops. And the reds are hematite-based and a mixture of hematite and lead hydroxide. The green was celadonite, and the yellows were both yellow earth, goethite-based and jarosite-based. Beyond the pigments, litharge rods, that is lead oxide rods, as well as amorphous metallic lead lumps were found at the site, indicating that metallurgical processes were carried out, including the reduction of lead oxide to metallic lead. And possibly this lead source could have been used also for pigment production. Now, the micromorphology, I won't really get into details about this, but I'm happy to share the work that has been published. In short, the micromorphology of the finds demonstrate that we have a low alkali starting mixture and a solid state synthesis. And the detection of tin in the analyzed samples may be indicative of the use of bronze as a copper source, possibly suggesting the recycling of copper alloys to produce Egyptian blue at the site. As you can see, not all the finds, about half of the finds were successfully produced, like the first one here, with the characteristic deep blue color, while some were partially successful. They had visible blue, but also other, like green color was visible, and some were completely unsuccessfully produced. And the analysis suggests that the unsuccessful production was governed by improper, let's say, starting materials and the limited control of the craftspeople over the raw materials that they were using, therefore reinforcing the hypothesis of recycling of materials. Beyond the production of the initially produced Egyptian blue pellets, the koan material demonstrates that the materialization of different tonalities of blue took place at the workshop through the further processing of the initially produced pellets. Microanalytical investigation of the finds suggests that 2 variations of the manufacturing process were carried out at the same site to produce different tones of blue. The koan workshop therefore demonstrates the complexity of Egyptian blue production, which might result into pellets of different composition, depending on the starting materials used. The ceramic vessels, the saggars, in which Egyptian blue pellets were placed during firing, according to Vitruvius's description, have been considered in general a very important factor in the production of Egyptian blue. However, no saggars have been found in the Koan workshop context, at least so far, and the finds that, as you can see, stand alone as individual pellets of about 3 centimeters across, as opposed to the lumped pellets from Memphis or other sites, and the cakes from earlier productions, suggests that the firing of the initially shaped paste of materials was carried out on a flat surface and not on a small saggar. When comparing now Kos to Puteoli, where the famous Vestorian workshop was established, we can observe that the two sites have some important common traits. Both places were ports, very important and big ports during the period of their thriving, with cultural and trade relationships with Alexandria, the mythic origin of Egyptian blue according to Vitruvius, and the establishment of pigment workshop close to ports would provide access to raw materials from distant sources, while the local treatment of raw materials to final products would possibly reduce the overall cost of the production. So the location is already quite important. Now, whether several small centers were established contemporaneously or if larger centers dominated are questions that need further research. But a common trait between all the sites that we went through today can be multi-crafting. In the first examples, we saw that Egyptian blue was produced alongside with faience, and then now with Ayani's example, we saw the connection with metallurgy, and also on Kos, we see that there is an exploitation of both pyrotechnological knowledge and certain common raw materials in the production. This is the concluding slide. So future archaeological discoveries may hopefully deepen our understanding of the organization of the production and trade of Egyptian blue. However, we know that such discoveries are rare and might never happen. And even if they do, archaeometric studies are particularly valuable since they can generate new knowledge and shed new light on the invisible traces of production. Interdisciplinary approaches, as it was underlined a lot today, are therefore crucial, and they should be guided by the material evidence and supported, if there is, by literary evidence, and can in this way deepen our understanding of Egyptian blue manufacturing and highlight variations in time and space. Thank you.
We now have Dr. Bruns from Copenhagen, who should be connected via Zoom. And we can see your screen. We cannot hear your voice.
All right.
We can.
Yes, can you hear me now?
We can hear you.
You can hear me? All right.
Yes.
Very good. Thank you. All right. So, first of all, I would like to start with thanking the organizers for arranging such an interesting conference on Egyptian blue and my fellow speakers for the very enlightening papers presented so far. And today I will present on the use and application of Egyptian blue in ancient art, focusing on the case of Roman Palmyra, which, as we shall see, presents a to me quite interesting and atypical case in its selective use and choice of blue pigments. I will thus not address the use of Egyptian blue in ancient Palmyrene art, but also its absence as well as its substitutes. I will not go into any details of the methods of analysis, particularly VIL photography, since we have already had experts specialized.
We cannot hear you very clearly, so if you maybe can speak closer to your microphone or slower.
Yes, I will try. Is this better? I'm sorry.
It sounds better. Let's try.
All right. I'll try to be as close to the microphone as possible, sorry. Well, I will not go into any details on the methods of analysis, particularly VIL, since we have already had expert specialized presentations on the topic. However, I will briefly present how we carry out polychromy research at the Glyptothek. The Glyptothek houses a large collection of ancient art, primarily Greco-Roman sculpture, a large Egyptian collection, as well as modern art. I work closely together with my colleague Jens Stenger, who you see on the image here, who's senior scientist at our laboratory. And we employ various methods of analysis depending on research questions, artifacts, and so on. And we always start out with non-invasive examination, including microscopy, MSI, and XRF. And this lays the basis for deciding on further invasive analysis, such as FTIR, Raman spectroscopy, SEM, and so on. And so far, we have examined around 100 ancient artworks in our collection.
We're not hearing you well.
I don't know what to do, sorry.
Yeah. Okay.
Yeah, I'm not sure what to do about it.
Maybe I would suggest that you speak slowly if you can, and let's try if that works to make it more.
All right, I'll give that a try. All right,
and maybe you can turn off your video, not that we don't want to see you, but that will
maybe that's
free bandwidth for the audio.
Yes. All right, I'll try again. What has really sparked my interest in Egyptian blue lately is that the pigment appears to be almost omnipresent. Based on my experience in the field of ancient polychromy during the past 7 years, it seems that all Mediterranean cultures employ Egyptian blue for their painted polychromy. Egyptian blue is attested from early periods onwards, from its emergence in the 3rd millennium BCE until late antiquity, in fact, even as late as in Italian paintings from the 16th century. Moreover, as you all know, Egyptian blue is not restricted to any specific medium or substrate, but used for the polychromy of marble, limestone, terracotta, wood, wall painting, and even in rare instances on textiles. Returning to Roman Palmyra, the case study of this presentation, Palmyra, ancient Tadmor, was an oasis city located in the middle of the Syrian desert near the Efka Spring, between the river Euphrates and the Mediterranean Sea, and thus strategically placed between the great empires of Rome and Parthia. The city was the most significant Syrian stop on the Silk Road and played a major role in the east-west caravan trade, and it developed into a large, prosperous city with numerous public monuments. Its heyday was in the first 3 centuries CE. Palmyra is probably best known for Queen Zenobia, the first and only female ruler of the city, who reigned at the end of the 3rd century CE. She rebelled against Roman supremacy and expanded the Palmyrene Empire by conquering Egypt as well as large parts of Asia Minor. And this was reciprocated by the Romans, who sacked the city during the reign of Emperor Aurelian in 272 CE. The Glyptothek possesses the largest collection of artifacts from Roman Palmyra outside of Syria. And the collection primarily comprises funerary sculptures, stucco fragments, and so-called banqueting tesserae, but it also includes altars, sculptural and inscriptional fragments, and a few artifacts of faience and glass. The funerary sculptures are the core of the collection, comprising more than 120 artifacts. And these include the most common types of Palmyrene funerary art, including stelae with full-figure portraits, loculus reliefs with half-figure bust portraits, banqueting reliefs, and fragments from sarcophagi. The collection of Palmyrene art was compiled primarily in the 1880s by the brewer and founder of the Glyptothek, Carl Jacobsen, through his contact with the Danish consul in Beirut, Julius Leudved. And the collection is one of the earliest collections of Palmyrene art in the Western world. In a 2018 survey of the collection of Palmyrene funerary portraits was carried out using VIL and visual examination. Based on this survey, 6 portraits were selected for closer analysis due to their particularly promising visible traces of polychromy. The chosen artifacts include different motifs and types and represent different chronological periods from about 150 to 250 CE. And the portraits consist of 4 loculus reliefs and 2 sarcophagus figures. They were examined with various analytical methods, including microscopy, ultraviolet UV fluorescence imaging, and VIL imaging, XRF, SEM-EDX, and FTIR. And this summer, 1 additional portrait was also examined with the same methods of analysis. Various pigments were detected in the polychromy, including lapis lazuli, pyromorphite, mimetite, yellow ochre, a red lake, lead carbonate, zinc oxide, bone black, and charcoal black. VIL imaging has not revealed any convincing traces of Egyptian blue on the portraits examined. In some cases, a few brightly luminescing particles are observed. However, they seem to be unrelated to the polychromy. Firstly, the distribution of the luminescing particles appear quite random. Many of the particles are found on heavily abraded areas that have never been painted. And secondly, no blue particles have been identified in the corresponding locations. And this would suggest that the luminescence observed is emitted by other materials with similar VIL properties to Egyptian blue. Another possibility is that single particles of Egyptian blue are present, although not detected by microscopy. And in this case, the random distributions point to contamination introduced in the workshop, the tomb, or most likely in the museum environment. The only visible traces of blue paint on any of the 6 sculptures are observed on the mantle of the female portrait 1150. The portrait represents a palmyrene woman and is carved in high relief. It was originally part of a sarcophagus lid, and the portrait has been stylistically dated to around 210 to 230 CE. The light blue-gray paint is attested in several places on the portrait, and there's no doubt that its application is intentional. An examination with a microscope reveals heterogeneous dusty blue paint traces with dark and bright blue particles. The identification of lapis lazuli in these traces was confirmed using Raman spectroscopy and SEM-EDX. Considering that the archaeological record contains numerous minor objects carved from lapis lazuli, there are astonishingly few known instances of its use as a pigment in antiquity. Thus, so far, the use of lapis lazuli as a pigment for painting has only been attested in a handful of instances, ranging from the 16th century BCE to the 2nd century CE. And this palmyrene example is thus only the 4th certain attestation of its kind in antiquity. The oldest example is a fragmented limestone statue of a queen from Thebes in Egypt from the 17th dynasty. And the second example is from a 13th century Greek Bronze Age wall painting from Gleb. The third example is a Greek marble pyxis from the second half of the 5th century BCE. Furthermore, it has been suggested that lapis lazuli was identified on a Gallo-Roman terracotta statuette from the 2nd century CE. And in addition, a few particles of lazurite have been identified in an Egyptian canvas painting from the 3rd or 4th century CE, but these particles were dismissed as contamination. And the digital representation you see to the right illustrates a probable original distribution of the blue paint on the portrait. So, this relief has several traces of green and blue paint distributed over the surface. Examples of paint traces are indicated on the slide, but many more are tested by visual inspection and microscopy. It was examined with VIL, which showed no indication of Egyptian blue. 3 samples from the greenish paint traces were taken and examined by FTIR September this year. And this showed that sample 1 of the greenish paint contained barium sulfate and Prussian blue. Sample 2 of the greenish paint contained barium sulfate, Prussian blue, and gypsum. Sample 3 of the greenish paint contained barium sulfate, Prussian blue, gypsum, quartz, and chalk. Moreover, the XRF shows zinc, barium, and sulfur, suggesting the presence of the dense white pigment lithophone, which is composed of a mixture of zinc sulfide, barium sulfate, with trace amounts of zinc oxide. And lithophone was first produced in 1874. Lithophone is an inert, transparent pigment, which is often used as a filler or as a base for lake pigments. And it was widely used in house paints in the first half of the 20th century. Thus, the paint preserved on 2776 is clearly modern, since Prussian blue was not discovered until 1707, and also due to the presence of lithophone, and then is when it appears to have been synthesized for the first time by the paint maker Johann Jakob Diesbach in Berlin. That the paint is in fact modern is quite surprising, since it has a stratigraphy that looks ancient. It's powdery and dry, and the pigments are not so finely grinded as in modern paint. Overall, it looks very different from what fresh gallery paint looks like. Moreover, the paint traces are clearly not accidental paint spatters, but also placed in depressions, such as you see in the horizontal ridge at the bottom of the relief to the right. And this obviously raises questions as to how, when, and why this paint got on the relief. And it shows how careful we should be when examining ancient artifacts and polychromy by visual examination only. And as a bonus info, I can mention that the relief was acquired by Harald Ingold, employed at the Glyptothek in 1929 from the art dealer Dr. Ziadeh in Beirut, in Lebanon. And most likely the paint traces ended up in the relief when in the possession of the art dealer or after entering the museum collections in 1929. So far, only few studies of palmarine polychromy has been published, and the thorough study of the wall paintings from the Tomb of the Three Brothers is to date the only comparative study available. It's published by Bousson et al. In 2015. The Tomb of the Three Brothers is a hypogeum located in the southwest necropolis at Palmyra. The wall paintings, dating to the 2nd century CE, and thus contemporary with the Palmyrene funerary portraits, were constructed using a variety of pigments, including red and yellow ochre, red and yellow oxide, carbon black, green earth, mimetite, and Egyptian blue. Moreover, huntite and dolomite were used to lighten the green hue in some places. Egyptian blue is attested on the south pilaster, rendering a woman with a child, as you see on the slide here. And here Egyptian blue is used for the child's light blue clothing, and it's mixed with an orange ochre. Egyptian blue is also attested in the painting on the 4th pillar on the western wall. And here Egyptian blue is used for the dark blue paint in the medallion, as you see centrally placed on the slide. By comparison with the funerary portraits under study here, it's clear that there are several overlaps in the choice of pigments, such as red and yellow ochres and possibly carbon black. This is not surprising, considering that these pigments were probably locally sourced and readily available. Yet there are also significant differences. As an example, the wall paintings use green earth, which is not attested on the portraits. However, the most fundamental difference lies in the choice of blue pigments for the various media. Egyptian blue was used for the wall paintings. However, this specific pigment is not attested on any of the portraits in the collection of the Glyptothek, which appear to have used ground lapis lazuli instead to render the blue color. And this I find to be a very interesting discovery, since Egyptian blue was widely used across the Roman Empire and also in Palmyra. Its absence from the polychromy of the funerary portraits is clearly intentional. There are thus clear discrepancies in the choice of pigments used for the polychromy in the various media. And the variation in blue pigments appears unrelated to chronology, since they're almost contemporary. Neither is it related to the motif, since in both the funerary portrait, 1150, and the wall painting on the south pilaster, the light blue colors are used to render clothing. The explanation should therefore be sought somewhere else, either in the different media, like portraiture in stone versus wall painting, or in the different artists working in these respective media. The motifs rendered in the tomb is a winged victory, the scene of Achilles disguised as a girl by his mother Thetis on the island of Skyros, as well as the abduction of Ganymede by the eagle of Zeus. In these paintings in the tomb are claimed to be clearly inspired by Greco-Roman iconography and contrast with the usual tomb decorations at the site. This could possibly be an indication that the wall paintings were done by itinerant artists or workmen, which could explain the differences in the choice of pigments between the wall paintings and the funerary portraits. However, this is based on very meager evidence and of course merits further investigations, particularly of Palmyrene wall paintings, which for now at least is a complicated task due to the current state of affairs in Syria. So this case study has shown that, interestingly, Egyptian blue has not been attested on the more than 20 or so Palmyrene portraits examined by VIL in the glyptothek, nor on the 7 thorough examined portraits. And in fact, lapis lazuli is to date still the only ancient blue pigment identified on Palmyrene sculpture. It's important to mention that all surveyed portraits have not been cleaned, but have preserved visible traces of polychromy. The overall absence of Egyptian blue in these portraits is surprising, since it's the sole blue pigment so far identified in ancient Palmyrene wall paintings and other interior decoration. Moreover, Egyptian blue was widely used in contemporary sculptural and architectural polychromy in other parts of the Roman Empire. The choice of lapis lazuli is surprising, since the stone consists of a mixture of minerals, which means that grinding it into a fine powder will result in a grayish blue tint, rather than the bright, deep blue indicative of the stone. The appearance of the ancient pigment made from grounded lapis lazuli was thus very far from the bright blue pigment known as ultramarine, used from the medieval period onwards. Moreover, during the Roman Empire, this pigment is considered as extremely expensive, since it was imported from Afghanistan. However, considering that the price of commodities rose about 100-fold from one end of the Silk Road to the other, lapis lazuli would have been more affordable in Palmyra than in Rome, for example. Nevertheless, considering that the cheaper alternative, Egyptian blue, was evidently used for interior decoration in Palmyra during the 2nd to the 3rd centuries, the choice of lapis lazuli for the portrait appears somewhat extravagant and puzzling. It is possible that the choice of lapis lazuli was not only a deliberate way of reflecting the prestigious character of the work, but also an indication of the existence of different workshops for wall paintings and portraits. Thus, knowledge of the specific constituents of the polychromy of an artwork can potentially provide insights into the coexistence of different workshops or artists at a given site. And although this case study is obviously only based on a little bit more than 20 artifacts and very limited comparative material, it does indicate a pattern which is very interesting to explore further. And I would therefore, of course, be extremely interested in knowing whether people have examined similar Palmyrene portraits in other museum collections worldwide, and whether or not they have discovered any use of Egyptian blue or other blue pigments. So thank you. And I really apologize for the poor sound.
Thank you, Dr. Brunt, for your contribution. Thank you very much. Now the next speaker is Professor Admir Masic from MIT. Admir, you know you're the one thing that stands between us and the coffee break.
I know, that's a challenge. I hope I will entertain enough so that our 20 minutes we spend in quality time. So, thank you very much for this invitation. It's really a great pleasure to see such an incredible group of people, and thank you, Antonio, for making me part of this symposium. I'm gonna talk about recent work that we have been doing at MIT together with colleagues here present in the room, as well as the others around the world. So I hope I can change the slide. Okay. So my group at MIT is trying to get inspiration from ancient materials and also biological materials to inspire, to design materials that would perform better compared to what we have ended up using after Industrial Revolution. So imagine that we start with the hypothesis that we have been doing better before introducing a series of new materials into our common lives. So you can see many different models here that we look into, and eventually we really aim to make this world better in terms of mainly sustainability of what we build, what we make, and again, make something that will guarantee a future of our civilization. So when we talk about the concept of antiquity-inspired materials, we basically go into places where these materials maybe lived for 2,000 years and then put them under our cool microscopes and spectroscopes and use any type of knowledge to then be able to not just, as I said, learn how, when, where questions, but also how can we use that knowledge to then design something for the future. The great example is definitely Roman concrete. And I don't think there is a better place than this here, venue of the conference, to talk about Roman concrete. And this was the first material we tackled in our work. Ancient Roman concrete lasts for thousands of years. What we build is guaranteed for 150 years. And you can see many examples of failure of modern concrete, whereas everything we see around here is built using a material that stands still. And the mission of this work indeed is to design something better, and indeed based on this work on ancient Roman concrete, we were able to test a hypothesis of self-healing in ancient materials, but test very much the closure of cracks in a modern ordinary Portland cement. And this is the startup that we just launched last year that actually translates this knowledge into real world. Very important to say is that because it's based on ancient technology, materials that we introduce are very cheap and available everywhere in the world. The key feature when you start to think of translating something into real world. All right, so we published a series of papers on this, but there are many other materials that are out there ready to be tackled and studied using analog approaches. And so today I will focus on Egyptian blue, and I mean, I don't want to repeat many of these concepts that we learned today already about Egyptian blue, and I will show this video that I took from a wonderful exhibit that was produced in Egyptian Museum, where the video describes ancient way of making Egyptian blue, and you see Toraka, we see a lot of details on taking essential small like elemental materials, mixing them in the mortar, and then most importantly then putting into a kiln. You will see in the video, and this operation then leads to melting of the material, and after slow cooling, eventually ended up in this composite of crystalline and amorphous vitreous matrix. So So now we have learned that, these materials are incredible in terms of emission in infrared, and these features are really of extreme interest for modern applications, considering that these things are nano sheets that eventually you can functionalize. You can do a lot of incredible things, and they are also emitting in. Here is Marco that we'll be talking later. And these nano sheets of cuprorivierite basically offer incredible opportunity to translate things into modern applications. And I have this educational project that I bring students to Italy, which is very exciting for them because many of them never been outside the States. But this is aiming also to bring them and expose them to these materials that eventually someone will be so inspired to help me in the lab to continue with some research. And this is Max Kessler that eventually went back to my lab and discovered an interesting feature. I will show you quickly what he discovered. So we have a Raman spectroscopy in the lab, and Raman spectroscopy is a technique that basically shines a laser, and molecules respond to this radiation in a way that they basically modulate radiation through vibrations, and this change in shift in energy eventually leads to a series of peaks in a spectrum if you collect that light after being filtered into a spectrum. And these spectra are actually fingerprints of your molecules that you identify. And you see you can really clearly differentiate many of these minerals. And you can do this for Egyptian blue as well. What Max came up with, he noticed that there was like a tail of a big emission that he would detect every time he would hit Egyptian blue. And when I saw that, I said, hey, this is interesting. This might be the luminescence, because we use a laser, generally green, red, infrared laser to excite. And if then this emits, and our CCD camera will detect it. And so we found a way to actually collect simultaneously the Raman molecular vibration fingerprint and emission luminescence in the same experiment. And now the question, can we maybe use that to go back and at the moment of making perhaps understand what people put into the mix. And so we partnered, of course, with the Egyptian Museum, Blu Egizio di Torino. They offered us the opportunity to look into these statuettes, the shaptis, and we were able to sample them, put into cross-section like we have seen today from Giacomo Chiari's presentation, where now, instead of collecting only Raman, we would collect also luminescence. And that allowed us, on the micron scale, sub-micron, because this is a confocal microscope eventually, we were able to differentiate grains that would emit luminescence and others that would not, and then work on the differentiation of vitreous material that was maybe, that was surrounding its part of Egyptian blue, because eventually Egyptian blue would crystallize. And so what we noticed here, we were, of course, noticed a lot of heterogeneity in the samples, which is definitely the evidence of different ways of purifying and processing these pigments. The cool thing about the technique itself is that each of these peaks eventually gives you a clear information about chemical environment of both glass and structure of both glass and Egyptian blue, and even tiny difference we're able to detect. Another technique that we applied was SCM-EDS, that is again aiming to kind of by plotting these ternary diagrams of calcium, silicon, and copper, perhaps to see differences based on the position of this spot on the ternary diagram. And of course, if you have a different chemical composition, these spots will move. And what we were able to do is, again, map on the micron scale, imaging the differences, chemical differences in different samples. And here, high-resolution chemical characterization provide indeed insights into structure and composition of ancient pigment. Ternary diagrams, representations of quantitative EDS data show different compositions between samples, and these differences can be related, of course, to the differences in different production workshops. Nevertheless, I was a little bit disappointed because I was really hoping to be more precise, more quantitative, all this. And this is where Sofia Mittmann comes in. Another year, another group of students in Italy, and Sofia was excited about Egyptian blue and went back to MIT, and she built really an incredible experimental approach that basically allowed us, for example, to study magnesium enrichment in the synthetic Egyptian blue mock-ups. The Parco would synthesize, Marco Nico would synthesize hundreds, thousands of these. So we picked some good ones and put under the microscope. And indeed, you can incredibly correlate all this information into a series of images that are especially, as I said, correlated. And so you have a composition, Raman, and luminescence all together overlapped. And this allows you to, for example, answer questions such as, is magnesium going into the Egyptian blue or not? And here we show some results that also we are hoping to publish soon, where you see magnesium is expelled from the Egyptian blue mineralizing, crystallizing in the mix, and this can be easily seen because there are sodium and magnesium rich regions that eventually do not emit luminescence and therefore do not present this amazing structure that we have seen from presentations and in the video. So this is really an important step forward in really kind of differentiating what happens during this process. And it would be nice now to see if magnesium, perhaps even in little numbers, maybe atoms go and substitute, nevertheless, in the structure. And so this is what we did. We tried to do atomic resolution scanning transmission electron microscopy that we are blessed to have in our MIT Nano at MIT. And these are the first results on Kramer Egyptian blue on the sheets that were exfoliated from Egyptian blue. And this is what we got. So this is a super high resolution imaging of Egyptian blue where you can see atoms of calcium and copper, how they are organized perfectly in the crystal lattice of cuproriverite, which is really exciting because we could start now thinking if we produce something, perhaps we will be able to see magnesium instead of calcium. That would be a little bit darker because lighter as an element. And what else we did here? What we really noticed, and this looks like a property, standard property, is that every time that you have a crystal, so these atoms here, there is a border interface where then it turns into amorphous. And this, if it's true, and if becomes systematically present in all Egyptian blue samples, might be a way to actually look into original materials that were used in production, because this Egyptian blue was crystallizing while we were cooling in the workshop our Egyptian blue. And if we see it as still Egyptian blue, means that this Egyptian blue was produced exactly at that moment of time, so T0. And now, if we assume that this amorphous is what is the glass, what is the trash that was expelled at the moment of crystallization, this might be an original time zero formula of our workshop. So we try to do this, quantify which elements are there, for example, at this interface here, and these are results, very encouraging, and this basically shows constant concentration of calcium, silicon, copper, and oxygen in Egyptian blue crystal. Of course, you see the atoms, they are perfect, but then starts to oscillate in the amorphous part, which eventually now is a matter of putting good students to work and have great samples to actually see the differences in the amorphous phase now, because this is the one that we would like to focus on eventually, to be able to see what was expelled. So what was the original composition that was melting in that kiln, okay? So one more point I want to make here. It's not always like we have seen here, we are shooting accelerated electrons on the sample. Degradation can occur, and this is something that we need to bear in mind. This is a copper particles, nanoparticles that we made at the nanoscale, so we are not damaging our samples so much. But still, we need to bear in mind when studying these samples. And I have now a great undergraduate student that will dedicate some time on this scanning electron transmission electron microscopy. And with that said, I want to close with saying that we are here always trying to improve our techniques, but I think the Bluenet shows the potential of interdisciplinary work that is the only way, I believe, to really push forward the science, and the only collaborative effort from all the partners in this network, I think, will be able to answer some important questions, not only of the past, but especially inspire the future, and perhaps design better solar cells, better catalysts, and anything that might come out from this work. So thank you so much, and I'm happy to answer questions if we have time. Okay, coffee break. We have even 3 minutes more.
They'll ask you questions at coffee break.
I like that one. Ecco, okay. Let's start over. That's good. I was okay, perfect. Here we go. So, it's a great pleasure to chair this session and help Antonio to move forward with the symposium. In this session, we'll have very interesting talks, especially about the new perspectives that definitely I share interest in. And as a first speaker, we have Alexandra Rodler from Austrian Academy of Sciences in Vienna, and we are looking forward to your talk. Your stage is yours.
Thank you very much for this introduction, and thanks for including my contribution for this exciting conference. So today I will present recent advances in the provenance analysis of Egyptian blue and some of the results of my ongoing work. With pigment provenance analysis, I would like to reveal whether local raw materials were used or not, and I hope to better understand the scale and organization of Egyptian blue production and trade networks. Because often only traces of the original polychromy remain, the analytical approaches in ancient polychromy research are usually focused on identification and characterization of pigments. As you can see here with the visualization of traces of Egyptian blue that was used for painting the sandal of this marble sculpture as part of the collection of the New Casper Bibliothek in Copenhagen, Denmark. So methods like invisible induced luminescence imaging, as we know and just heard earlier today, are incredibly helpful for detecting traces of color and characterizing ancient polychromy. Recently, the geochemical provenance analysis of pigments and colorants added new layers to ancient polychromy research, and I will try to show you with the first rough layout how this can be useful for better understanding the life history of Egyptian blue and the context of this remarkable pigment in the past. So my work on ancient polychromy started at the wonderful New Casper Bibliothek in Copenhagen, Denmark, where I joined the polychromy research group for a project focused on identifying the provenance of Egyptian blue pigments. And for pigment provenance analysis, I used the trace element composition and specifically lead isotope composition of pigments. And this can show us when geological materials, such as copper minerals, were formed, geologically speaking. And because ore deposits have different ages and formation histories, we can use this to tell them apart. Now, when using lead isotopes for pigment provenance studies, we work with the understanding that technological processes are not expected to change the lead isotope composition between the raw material and the pigments. This has been tested for ancient glass and lead-based pigments, and we compare to large lead isotope databases to exclude the least likely source areas. Besides the mineralogical and petrographic information, we also include trace elements and recently also rare earth elements to support the lead isotope-based provenance evaluation. The sample lead isotope data is then compared to large lead isotope databases where the least likely source area is excluded, as I said before, and the matching source areas are then plotted with lead isotope biplots, like you can see here now. So I will not bore you all too much with the basics of this, and you're very welcome to ask me later. But what you can see here, so usually we have lead 206 over 204, on the x-axis, and then lead 207 and 208 over 204 on the y-axis. So it's usually in this double plot. It's not that easy to hear me. Okay, thank you. So with this, we can include 3 dimensions for evaluating the raw material provenance and how well a source area matches the pigment samples. Also, we can see the spread of ore deposits and the alignment of samples and how this fits with reference data. A crucial factor is also the historic archaeological context of the artifacts, as you're aware, where the samples were taken. And here below now are a few examples that I will show to use you some of the recent advances in Egyptian blue provenance research, spanning from the 4th century BC to the 2nd century AD and going from Egypt to Italy and to the Roman province Noricum. So with this in mind, just a quick overview over the currently known Egyptian blue production sites of the Roman and Hellenistic periods. These sites were already mentioned today, and of course you know Memphis, and then we heard about Kos and also of the Bay of Naples. So this is where my ongoing work contributes to better understanding where raw materials for Egyptian blue production came from and how this can connect source areas between pigment production and places of pigment use. So for example, if there was use of local resources and therefore potentially local production that we cannot see in the archaeological record. For the first example, I start with the Etruscan Antifixes. These terracotta roof ornaments were mold-made and used on the outside of houses. And these 3 artifacts here are all part of the collection of the New Casper Bibliothek. All were used for the same building, and 2 of them might have been made from the same mold. And the Egyptian blue samples were collected from all 3 antifixes for analyzing the copper provenance with lead isotope analysis. Okay. So here you see the lead isotope biplots, like I mentioned before. The colorful clusters in the background are the reference data that we compare to, and the star is the sample. And the ellipses show the Egyptian blue, for this case, was most likely from the Aegean, the copper for making this. And then the next sample, apologies, I didn't jump on. So now you can see this. So for this example, we most likely propose that Aegean copper was used. Then the next one, very likely from Ibuna, so from Bulgaria, was the copper for making this Egyptian blue. And then the last one from Iberian sources. Okay, so, so now altogether, what this gives us is quite a complex picture of the provenance of copper used for making Egyptian blue for these artifacts, and all at the time when we actually do not know any Egyptian blue production workshops. So at this point, we know that copper from various source areas was used for producing Egyptian blue, that was then used for painting the antifixes of the Citerian house. This means that Egyptian blue production was supplied by a far-reaching copper market and could also mean that Egyptian blue production was widespread and part of a well-integrated metal and probably also glass trading and processing industry. Okay, so next, yes. We're also looking at an artifact from Egyptian blue production workshop at Memphis. Yeah, that's helpful, thanks. Yeah. So here, two examples. They were excavated in 1910 and dated to the 1st century BC. They're also part of the archaeological collection of the New Casper Glyptothek. So here again, the lead isotope biploid, like I showed you before already. And here, in this case, the sample is the yellow star. So it's two samples, and they're so close together that they're just overlying. And we compare again to possible copper source areas. So first, in orange, this time I made ellipses that are a little bit easier to see. And in gray, yes, you see Italian sources. Sorry, I'm technologically challenged. Okay, let's go on. And then in green is from the Araba Peninsula. And now in purple, you see Aegean sources. So for this, we propose that copper from Aegean sources was used for Egyptian blue production in Memphis. So the trade already existed between the Aegean and Egypt at this time, we know this, and was active, and possibly this far-reaching metal network supplied copper for Egyptian blue production at the Memphis facility in the 1st century BC. So to follow with this, we continue with the 1st century BC, but changed to Italy, where this artifact, the Campania relief, named after its collector, was painted with Egyptian blue sometime between 50 BC to 60 AD. Okay, so at first 3 samples were collected and combined for one lead isotope analysis. The 3 samples are here in blue points. So they were pooled together for one analysis, and it gave us a bit of a mixed signal. So what you see here, this potential source area was in Iberian copper, all the way to the Bay of Naples, potentially, where the Egyptian blue was then produced and then used for the artifact. But I wanted to have a look at this again to see if we could refine the provenance evaluation a bit better. So I asked my bachelor thesis student at the Free Universität Brussels to just treat 4 samples as individual samples and analyze them as individual lead isotope samples. And the results, you can see here, so the plot a little bit better, so we can see the alignment of the samples better and also how they match with the reference data. So this increased sample quantity allowed us then to propose that copper from the Eastern Alps was likely used instead of the Iberian. That was a bit of a mixed signature where we weren't quite sure if it's really correct. Okay, so to add to refining sample strategy with several samples per paint layer, we also recently tested a new sampling method here. It used a cotton swab suffused with low concentrated nitric acid. To collect Egyptian blue from this artifact from Memphis that you already saw before. So I sampled previously already analyzed samples, and I collected in time intervals of 10, 30, and 90 seconds, and also in duplicates, of course, to compare to the previous results and also to see how reliable these results are. So just to cut it short, the results are reliable. We can use them. The 10 seconds already give us good data with spectrometric analysis by TIMS. And we could also reproduce the results that we had before. So this is a new method that I hope to apply also to other pigments in the future and refine a bit further. Then with my current project, I'm investigating the provenance of Egyptian blue pigments from the Roman province Noricum. It's almost present-day Austria, as you can see up here. So after it became part of the empire in 16 AD. So here I analyzed whether Egyptian blue used for painting walls north of Italy was supplied with Egyptian blue produced in Italy, or whether there was a local production. Because local resources were available, they could have made Egyptian blue there as well. There's currently no evidence of Egyptian blue production in Noricum, but raw materials were available, and there were definitely secondary workshops, we know that. So I mainly use samples from Roman wall painting fragments and compare between different Roman sites across Noricum. These are here with the blue points on the tiny map. And also compare to central Italy. And besides Egyptian blue from wall paintings, I'm also looking at Egyptian blue pellets that were found in Noricum. So for investigating trade and local production, I'm looking at the locally available resources such as calcium-rich sands and copper that might have been used for Egyptian blue production there. The sands across Austria have been collected by the Austrian Monuments Authority for heritage science projects, and I use this collection as a reference. And copper reference data is already available in large lead isotope databases. So I investigate the provenance of the copper compound with lead isotopes as before, and the provenance of sand with strontium isotopes, but today I will only show you the lead isotopes because the strontium isotope work is still ongoing. So here are the lead isotope biplots for samples from Noricum. So the Noric Egyptian blue samples are plotted as stars again. They show good overlap with the copper ore deposits from Eastern Alps, Switzerland, and also Slovakia, so with Central European copper ore deposits. And also there seems to be two subgroups, with the bulk in the left ellipse and the smallest subset for here in the smaller cycle. So this second smallest subset still matches Central European copper ores, here also from Switzerland, for example, and from Italy, but there could have been a slight change in supply of materials between the 1st and the 2nd century AD. So when comparing the provenance information with information about the morphology and chemical composition of Egyptian blue pellets, here, for example, with microprobe analysis for Noric examples on top, and then below are examples from Austria, and then also an Iron Age example from Karkamış in Turkey. So you can see that the Karkamış sample here is a very pure and homogeneous Egyptian blue, which is also indicated by XRD analysis. And overall, the cuproid crystals of all 5 samples have a consistent stoichiometry and ratio between the calcium, copper, and silica, and the samples from Noricum in Italy are strikingly similar. So combined with the provenance of copper, this sample, the similar composition of Italian and Noric Egyptian blue pellets might indicate that the Central European copper, for example, from the East Alps, was used for Egyptian blue production in Italy, and then the Italian-made Egyptian blue was traded back to Noricum. So to put this in context, for the 1st century BC to AD, this fits with the small subset of samples from Noricum. We have results for Egyptian blue from Memphis that was made with Aegean copper, and then the Egyptian blue used for the Campania relief that I showed you earlier that was made from East Alpine copper, very likely, and at least in the last Egyptian blue from Noricum, the wall paintings and also the pellets from Noricum were made from Central European copper, so from the Eastern Alps again, or from Slovenia or Switzerland. And there was a change in supply between the 1st century AD and later periods in Noricum. So when comparing to the Noric Egyptian blue samples, we can see that there was probably a production using Central European copper in Italy that then supplied Noricum with Egyptian blue. While there was probably still an existing Egyptian blue production in Egypt with Aegean copper. Okay, so as we know, the ancient world was fascinated by color and it proposed that material quality and also provenance mattered. And recently growing attention shows that pigments can provide a unique perspective on the interaction of humans both with the natural environment and between societies. So yet we currently know fairly little about where resources came from, where they were processed and traded. And I have recently submitted a research proposal called Color in a New Light, Origins, Trade and Cultural Significance of Ancient Pigments for an EC starting grant call, and had the interview last week. So if this is possible to go forward, then the idea is to spend the next 5 years evaluating these pigment networks, how this relates, so how the different trade points fit together and how the production fits in with the sources of raw materials. And this will be guided by Egyptian blue, because it's such a remarkable pigment and connects several industries and material supply chains. And by identifying the raw material provenance and processing for making Egyptian blue, amongst other pigments, I hope to reveal new information about the exploitation and circulation of resources, to provide a first layout of this pigment trade and production network for future work to build upon, of course, and also hopefully future collaborations. All right, and with this, thanks. My colleagues and to you for your attention.
Wonderful. Thank you for being on time. Actually, we do have a few minutes for questions if someone wants to ask. Yeah, I caught you unprepared. All right, if no questions, let's move. No questions, let's move forward. Okay. Thank you very much for this remarkable presentation. And next speaker is Maurizio Aceto from Università degli Studi del Piemonte Orientale. I'm very happy chair session where Maurizio is a speaker, because Maurizio is probably one of the first people that I know.
That's why I am so old.
Okay, let's just say you are a great member of this community, so I'm very much looking forward to your talk. Thank you.
Thank you very much. So I'm going to bring you some evidences, or I should say, indeed, a few evidences, as you will see, of a non-traditional manufacture of the pigment. As you know, nearly all the Egyptian blue samples found in the studies were probably made from copper minerals, or most probably copper alloys like bronze. How can we say this? Because of course, of hundreds of elemental analysis, there is a huge work by El Goresi, where indeed hundreds of data are available, and according to El Goresi, it seems like there are three phases concerning the source of copper. The first phase is using scraping of arsenical bronze. The second phase is pure bronze, that is copper tin, and a third phase with bronze with some lead. That is what diagnostics say to us. As to the Roman age, the situation is quite similar indeed. Most of the analytical evidences say that bronze was most probably the source. There are a few data that certify the use of pure copper, for example, the work by Lazzarini and Verità, but nothing beyond these possibilities. So what I propose you is these three cases. I am aware that I am working on a sort of glass climbing, but this is what analysis tells us. Three cases in which we found some evidences of a preparation of the Egyptian blue from a copper-zinc alloy. Two of them are on manuscripts, from a pigment used on manuscripts, and the third one is, the latest also, is from the mural paintings of Castel Sepio. As you will see, the comparison is good because the ratio between copper and zinc is almost the same. But unfortunately, these three cases are very different from the historical, geographic, and let's say practical point of view. So it's very easy to have some reasonable conclusions. That's why I am here to ask your help, indeed, to interpret this data. So the first case is the mural paintings in Castel Sepio, where there are large areas made in Egyptian blue, pure Egyptian blue, mixed with some yellow pigment to obtain the green. The painting cycles is dated to the 9th to 10th century. The painters were, if not coming from, at least influenced by the Byzantine tradition. And this is what we found in the blue areas. The result is copper zinc 4:1. And this is quite constant in all the blue areas. So it looks like is a reliable data from the analytical point of view, 4:1, which is a typical composition of brass. The second case is the Ashburnham Pentateuch. It's a very important manuscript dating from the 6th century, kept in the Bibliothèque Nationale de France in Paris. It is apparently another point of the world the art historians are not do not agree on the origin of the manuscript. It can come from Spain, from northern Africa, from northern Italy, from Rome. There is no agreement, so it's very difficult to compare the Ashburn and Pentateuch with Castelsepio paintings. But at any rate, the point is that, again, the blue area were made in Egyptian blue. There is a somewhat strange use of Egyptian blue, for example, for this background, as you can see, but also from some coats of, I can say, as you say, important figures. So this manuscript is unusual because Egyptian blue is the main blue pigment. This is very rare as far as manuscripts are concerned. And if you see the results of the XRF data, here you can see a light blue, that is a dark blue, but the result is the same. Again, copper to zinc 4:1, exactly the same ratio among them, and with the same with as Castelsepio. Of course, the light blue has more lead because it's apparently mixed with lead white. And the third case is 7th century, is a chronicon by Orosius, kept at the Biblioteca Ambrosiana in Milan. According to the scholars, it comes from Bobbio, an important abbey in northern Italy, founded by San Colombano, a monk coming from Ireland. This page at folio 1 verso has a decoration which is not insular indeed, so most probably the decoration is later, was added later. But at any rate, the point is that we have again Egyptian blue, as you can see, a very strange use again. And again, we have, as you can see, there are some remains still visible under the microscope. The point is that we have again the same result. Copper to zinc 4:1. I was talking with Marco Nicola before. He suggested me another case, a fourth case, coming from a study of a church in Hierapolis in Turkey. It was published a few years ago by Vettori and Bracci, and they had the same result. I mean, they published an XRF spectrum where there is apparently copper and zinc, and it seems like the same ratio. I'm saying it seems like because they didn't yield a quantitative result. We don't know why. We discussed it of this, but the authors just say that there is Egyptian blue and nothing about the composition. But we can say there are 4 cases. So now, let's try to do some consideration. I am aware that 4 cases is not that much, but at any rate, let's try to understand why, where, and when this strange production was made. The first question is the easiest: how they made. As Marco suggested me, maybe the use of brass can act as an additional flux instead of natron. And this could help in answering to the question why. Maybe as a consequence of the shortage in the trade of natron, which seems to occur in the very same period. It should be maybe 6th, 7th century. So it seems like these findings are compatible with that event. So when could be as a consequence of that phenomenon? The most difficult question is where, because as you can understand, Castelsepio in Lombardy let's say, Northern Africa, Bobbio, Turkey, have nothing in common. So it's not possible to say that non-conventional procedure was made firstly in. I'm not the one who is going to answer to this question. Of course, we need more evidences. For example, we should do elemental analysis on the other evidences of Egyptian blue in manuscripts. They are very few. Indeed, I can say they are not more than 20, 25 up to now. This is one of the first, the Goddess Calca Evangeliari in Paris, but the authors didn't make XRF analysis. There is the Vienna Genesis. In the Vienna Genesis, we found Egyptian blue as, let's say, a contamination of lapis lazuli. You can see the Ville image is not that brilliant, so I interpreted these results as lapis lazuli plus a small amount of Egyptian blue. I made XRF semi-DX analysis on the grains of Egyptian blue, and it was just copper. So not that kind of Egyptian blue. We have the Trinity Rabanus. This was analyzed by Paola Ricciardi in Cambridge, and she didn't find any other metal than copper. And there are some identification by Andrew Beebe, working in Durham. They identified at least 20 manuscripts with Egyptian blue, and they are trying to add elemental information. The interesting thing is that all these manuscripts containing Egyptian blue as a main blue pigment were made in England, or at least in the UK. So I think we have to wait for more data in order to say something more reliable than what is up to now. Thank you very much.
Thank you very much, Maurizio. So I learned that we don't have time for questions, so we will move immediately to the next presentation, and I'm glad to introduce Gabriele Selvaggio, who will be talking about ancient pigments for novel technologies, nano sheets for biophotonics. Selvaggio is from the Ruhr University in Bochum, Germany. Thank you.
So, thank you very much for the introduction. Buonasera, good evening, guten Abend, we can say. I have to say before starting, it's truly a great honor to be here, because I'm able to give this talk in such an amazing venue and with people, the biggest people of the Egyptian blue field in front of me, so it's truly a great honor. And again, thank you very much to the organizers for inviting me here. In the next minutes, as said, it will be my pleasure to explain to you how ancient pigments such as Egyptian blue, but also Han blue and Han purple, can be developed into novel nanomaterials, two-dimensional nanomaterials, nano sheets, which have really high promises for multiple applications, especially in the case of biophotonics. So, how do we get from bulk to nano? First, I want you to focus on this. Of course, for obvious reasons, I will not introduce the players. I just want to mention that always at conferences, I like to start mentioning the history, because I find these pigments really fascinating. Han blue and Han purple were developed later in China compared to Egyptian blue, and you can find Han purple, for example, in the terracotta army in Xi'an. These are the main players on my PhD, and they share several things, starting from the crystal structure. Crystal structure that was very nicely described by Professor Chiari earlier. In the case of Egyptian blue, but also Han blue and Han purple, we deal with layered silicates. Therefore, silicates which are displaying layers, so silicate tetraeder displayed in layers, and these layers are held together quite weakly by either calcium or barium ions. And in this way, these materials are prone to be exfoliated into 2D materials. The quite funny thing, in my opinion, is that it's extremely easy to exfoliate these materials. One can also do this by simply stirring these powders in hot water for 2 weeks, and you get already 2D exfoliated material. There are also other methods which employ, for example, tip sonication or bath sonication, or you could move towards the geology direction, so use some, for example, wet ball milling. In the end, what I want to say is that if you manage to not only exfoliate the material in this way, but also to decrease significantly the lateral sizes of these structures, you can yield two-dimensional nano materials, nano sheets. And these are the main players of my PhD. So from now onwards, basically, I will just speak about nano sheets of Egyptian blue, Han blue, and Han purple. A first thing still, however, about the bulk materials. Well, even here, Professor Veri earlier described perfectly the properties of Egyptian blue and mentioned also that they're given by the presence of the copper ion as color centers. And these are shared elements in Han blue, Han purple, and Egyptian blue. Therefore, they share photophysical properties. These photophysical properties can be nicely described in so-called 2D excitation emission spectra, which show Egyptian blue, Han blue, and Han purple in this case. And you can see here that typically you excite these materials in a broad range in the visible, and above all, that you can get a clear near-infrared emission, which has center wavelengths between 920 and 960 nanometers, roughly. Furthermore, as mentioned earlier in previous talks, as we said, we have long lifetimes in all three cases, and quantum yields which are very high, especially in the case of Egyptian blue. And these are the bulk properties, right? But now the question is, what happens when these materials are exfoliated into nanosheets? So when we deal with nanomaterials, you can already tell by yourself that nothing significant really happens in terms of fluorescence properties. So the fluorescence in the near-infrared is preserved in the nanosheet form. And this means you can get very small materials without giving up on the most important property of Egyptian blue, Han blue, and Han purple, which is the fluorescence. And this allows a plethora of applications, as I will show in the next slide. This is an overview figure from the review we recently wrote about nanosheets of Egyptian blue, Han blue, and Han purple. The thing I want to say, which I find kind of amusing normally, is that we deal with materials which are in the bulk form extremely old. I mean, they're really ancient pigments, as we all know. However, their use in nanotechnology is very young. Therefore, several studies have focused on investigating photophysical properties of these materials. For example, how does the fluorescence scale with size? Furthermore, other studies have shown that these materials share, for example, a very bright fluorescence, which allows a very easy remote detection, therefore without the use of a microscope. And these were employed, for example, also in imaging in plants. Furthermore, there is also a clear potential of these nanosheets in terms of lifetime engineering, if you remember also what Professor Comelli mentioned earlier during the day. There were then other works done by other research groups which show that, for example, you can exploit the typical high aspect ratio of Egyptian blue nanosheets, so this typical 2D geometry, to perform selective binding, more specifically selective enrichment of multiphosphopeptides, which is of high interest for mass spectrometry. Other works, on the other side, exploited the really stable fluorescence of Egyptian blue nanosheets as a reference signal for ratiometric sensing of bacteria within the frame of smart implants, for example, so a clear biotech application. Other works instead have focused on biophotonics applications, which I will describe more in detail in the next slides. Other groups have demonstrated the use of Egyptian blue nanosheets in multifunctional biocomposites, meaning that they could embed nanosheets of Egyptian blue in scaffolds, polymeric scaffolds, and these were then put in contact with cancer cells, and the nanosheets, which are known to have a high photothermal conversion efficiency, could be could be, no problem, were able to heat up the cells significantly till they were basically killing the cells, and at the same time released ions, bioactive ions, were able also to promote angiogenesis. Therefore, it's not just a matter of killing the bad cells, but also promoting beneficial therapy. And then, last but not least, there are completely different applications which are possible with nanosheets. For example, smart inking is possible. Also, latent finger mark detection, so basically CSI, crime scene investigation things. You can do it with the nanosheets of Egyptian blue. And also energy storage applications, as probably Dr. Nicola will explain later on. You can use nanosheets of Egyptian blue for lithium-ion batteries, but also for luminescent solar concentrators. So this is to say you can do so many things with these nanomaterials. And what I am very proud to say is that I worked in a group which managed to significantly contribute to several of these directions in the bioimaging field, as already mentioned earlier. And given the time restraints, of course, I will just show you a few results. So fundamental photophysical insights and a few examples of biophotonics. So given that this is definitely not the topic of this conference, I have to quickly open a bracket here to describe why bioimaging is good if done in the near-infrared wavelengths. To understand that, you have to imagine that you're a photon, and a photon which is shining towards biological tissue, and in this biological tissue you have your fluorophore, and then the fluorophore emits fluorescence towards a detector. So the question is, what happens to the photon on its way to the fluorophore and then towards the detector? Many things happen. For example, tissue scattering, tissue autofluorescence, tissue absorption. And what I want to convince you about is that if you design fluorophores that work in the near infrared and not in the visible, for example, you can get a lot of benefits, including, indeed, low tissue scattering. If you notice here, we have wavelengths in the x-axis. This is a typical visible region till 700 nanometers. And from 700 nanometers onwards, you have the near infrared 1 and near infrared 2 regions. And you see the tissue scattering is decreasing with increasing wavelengths. And similar conclusions can be also drawn for absorption of light by blood, absorption of light by water, and also tissue autofluorescence. Therefore, with this, I want to say that if you design fluorophores that work in the near infrared, you can gain higher tissue penetration and better contrast, as is shown, for example, in this very famous case study of a through-skull imaging of a mouse. And you see a clear benefit in contrast and resolution if you work on the more far end of the near-infrared region. What players do we have out there so far? So what fluorophores have been established? So in general, near-infrared bioimaging is a young field. So I'm showing now just the latest decades to give you a bit of a context. We have one-dimensional nanomaterials, single-walled carbon nanotubes, for example. We have zero-dimensional nanomaterials, so quantum dots and rare earth nanoparticles as well. And you also have organic-based systems too. All with pros and cons, all very successful for several applications, but the question is, what can we design which can become, in the end, the perfect fluorophore? What is the holy grail of a fluorophore which works in the near-infrared? And to do that, to design the perfect fluorophore, you have to keep in mind the challenges, which are photostability. You want the material to be photostable. Biocompatibility, of course, is very important. The sizes should be as small as possible in most cases. The brightness should be high enough to allow easy detection. And lifetime engineering, of course, would be nice if possible. And last but not least, the features, the optical features, would be nice if we could actually tune them. And with these limitations in mind, this list of challenges, what I want to convince you about is that nanosheets of Egyptian blue, Han blue, and Han purple, but specifically nanosheets of Egyptian blue, are really promising candidates as near-infrared fluorophores. So now let's dive into some results about, again, nanosheets of Egyptian blue mostly as novel near-infrared fluorophores for bioimaging. So we said earlier, after exfoliation, the fluorescence is preserved, as you can see here in this 2D spectrum. But then you might ask yourself, how do these nanosheets really look like when you image them in a near-infrared microscope? They look like these fluorescent spots, and if you keep in mind the scale bar, you might notice that these are in most cases resolution limited spots. And this means that given Abbe's law for resolution limit, you cannot resolve spots below 500 nanometers roughly. So what I did to try to, let's say, bypass this physical limitation and understand how small we can get without giving up on the fluorescence, I performed correlative measurements, and I followed two different approaches. One was a direct approach, which basically consisted in imaging the same nanosheets in two different microscopes, so our near-infrared microscope and also a scanning electron microscope, and also an indirect approach, which is based on particle tracking of the fluorescence of the nanosheets in viscous medium. And both datasets show the same very, very important result, that is that the fluorescence is retained down to just few tenths of nanometers. This means that you can really get very, very small and still get materials which are still fluorescent. And this is, if you remember the red box of challenges on the voice size, you can now put a clear tick because this means you can really go very small and not worry about losing the fluorescence. Another tick is regarding photostability. So if you remember, this was the first voice of this challenges red box. And you see here, by increasing tip sonication time, and therefore yielding smaller and smaller nanosheets, you don't get any difference in the emission profile, meaning that you don't get any peak shift at all of the emission wavelength. Furthermore, photobleaching is not happening in the case of Egyptian blue. This is a typical phenomena mostly occurring for organic fluorophores. And you see here, you can image nanosheets of Egyptian blue for up to 2 hours without any significant difference in the intensity. And this, together with the previous data set, really highlights the high photostability of these materials as novel near-infrared fluorophores. Now, given the time restraints, I cannot cover the other ticks of the red box, but of course, these were all addressed in our works. We can discuss them privately, of course. I will just show some examples of biophotonics, biophotonics applications, starting with in vivo fluorescence microscopy of Egyptian blue nanosheets into embryos of fruit flies. You might ask yourself, why fruit flies? Actually, fruit flies are very interesting biological systems for developmental studies, which can tell us ultimately also information about how our own tissue really works. So what was done here with a collaboration partner was to introduce nanosheets of Egyptian blue into Drosophila embryo in developmental stage, so while they were still growing. And these were imaged in our microscope, and you see the membrane of one embryo shown here, and these green blobs are nuclei of this embryo, which were genetically modified so to express a green fluorescent protein. And here, in this black box, you apparently see nothing, but actually, and you probably really don't see anything because of the beamer, but you have to believe me, there are 2 red spots here, which are the nanosheets of Egyptian blue. And that's one of the main advantages of working in the near-infrared, that you get low to none autofluorescence, therefore very high contrast when you do bioimaging. And thanks to the properties that we mentioned earlier of Egyptian blue nanosheets, that is, that these nanosheets don't bleach, we were able to image them on a long term and perform particle tracking while these embryos were growing. And in this way, with particle tracking tools, it was possible to identify active processes ongoing in the embryo. And this is just a proof of principle application that shows that you can use Egyptian blue nanosheets as near-infrared fluorophores for in vivo fluorescence microscopy. Next, the last result I will show, I would like to show much more, but of course the time is short, is actually the most recent one that was done in our lab. We performed surface functionalization of the Egyptian blue nanosheets for targeted bioimaging and more. We relied on an existing protocol, modified it, and applied it on Egyptian blue nanosheets. And this is a protocol which relies on silicon hydrogen activation by hydrosilanes. And this is a very versatile protocol because you can covalently graft onto the surface of the nanosheets multiple R groups of diverse chemical nature. There is a huge library about them. And also the reaction happens in 5 minutes, so it's really, really fast and at room temperature, therefore, of course, appealing for this reason too. And it leads to hydrogen evolution, so you can see the bubbling while the reaction runs to check if it's really happening or not. Furthermore, it is compatible to several analytical tools. Therefore, you can get seriously many confirmations from different angles that your chemistry is applicable on Egyptian blue nanosheets. And what we did was therefore to work with two hydrosilanes with two different R groups. The first one was pyrene. Pyrene is an aromatic molecule which is known to emit fluorescence in the visible. And this was done in such a way to perform colocalization experiments. So basically to validate the method and see if this really worked. And next to that, one check which had to be done, of course, was if the near-infrared fluorescence of Egyptian blue was preserved after this chemistry, because otherwise, of course, we lose the interest in this chemistry. And this was indeed the case. The near-infrared fluorescence is untouched by this chemistry. And in the last part, we repeated the reaction with a different hydrosilane, with a different R group, with an alkyl chain ending with a carboxy group. And this allowed a proof of principle bioapplication of targeted bioimaging. I will jump directly to this. What was done here, so you imagine you have nanosheets of Egyptian blue with carboxyl groups now covalently bonded on the surface. And what we did was to conjugate on these nanosheets folic acid, which is vitamin B9. And in this way, this conjugated structure was then introduced into cell lines, so cancer cell lines, HeLa cells, which are known to express the folate receptor on the membrane. Therefore, the idea is to target these receptors with the folic acid bond onto the nanosheets and do colocalized imaging, so targeted bioimaging. And as you see here in grayscale, these are the cells, and the red spots are nanosheets of Egyptian blue. And compared to the control, there was a significant difference in terms of colocalization, meaning that we were able to perform targeted bioimaging with functionalized nanosheets of Egyptian blue. And given the versatile chemistry of this approach, this opens up to several applications in the targeted direction, not just bioimaging itself. And with this, I am concluding. I hope I'm good in time. In a nutshell, what did we do? So we were able to establish nanosheets of Egyptian blue, Han blue, and Han purple as novel multifunctional platforms for biophotonics. And we were able also to covalently surface functionalize the surface of these nanosheets for a plethora now of targeted applications. And since we were in Bluenet, we have to keep an eye, of course, also towards the future. Therefore, what I think would make sense for sure would be to focus on further optimization of the exfoliation. Size fluorescence correlation studies could be observed more in detail. And also quantum yield measurements could really shed a lot of light on the photophysics of these materials. Novel sensing concepts could also be tested with strain sensors and lifetime sensors. And last but not least, as mentioned, we should now try several targeted applications, given that this chemistry now really allows them. And there is more to that, but I will end up here. I really want to thank all the past and current members of the Cruz Lab, specifically, of course, Professor Sebastian Cruz, for allowing me to get to know the wonders of Egyptian blue. And I want to thank the research groups we collaborate with, the collaboration partners, graduate school, research funds, the Bluenet community for allowing me to be part of this family, of this newly formed family. And in general, thank you all for your kind attention. Thank you.
Perfect. Thank you so much, Gabriele. And we have a last speaker of the session. It's a great pleasure to introduce friend and colleague Marco Nicola to close this session with his presentation entitled "The Ancient Pigments, Egyptian Blue, Chinese Blue, and Related Two-Dimensional Silicates from Antiquity to Future Technologies." The floor is yours, Marco.
Good evening. Thank you all for this beautiful, really beautiful day. And I thank a lot also Gabriele Selvaggio that made this futuristic approach into Egyptian blue that give rise literally to a number of new idea and enthusiasm for all. But going through the presentation of this idea, what have we realized? We have realized that there is time for general review. Why? Why? Because it's time that the last really complete general review has been released. And that probably was this. There are also few others, but I think that the really encyclopedic and complete and comprehensive last review was the one by Riederer, and that was published in Artist Pigments by chance, or by Fitzhugh, that was also the discoverer of Chinese blue and Chinese purple. 25 years have passed from then, so it's time. But first of all, it's Bluenet, the new opportunity. So we have the opportunity to draw again a state of the art at the beginning of this new experience that is Bluenet. And so why there is this need? I think because we need to maybe better describe the relationship of Egyptian blue with related materials on different point of view, because you can have material related, for instance, chemically, or maybe by the technical kind of production, or maybe because they have the same function. So there are many possible approach for this. We have to update data because, as for instance Christian Greco highlight, there is this thing about the fact that Egyptian blue was Egyptian, is Mesopotamian or whatsoever. So now we have new information, we need to add them. And we have also new hypotheses and theories, highlighting of controversial points, description of new features, suggestion of future research, and in-depth, and also by bibliographical reference. Each of these points will be treated by this presentation, so no worry. And all this research will be released, and is almost ready, so it's will be released very soon in the journal of Accademia dei Lincei, and will be, we hope, a new help for any researcher that want to be engaged with Egyptian blue. And so also another idea is this incredible photo, for instance. So we have natural copper riverite that we can directly observe, and we have a better understanding of the way it grows, for instance. So also to make it possible to find this kind of material, we think is important. So first of all, relationship with related materials. As you know, there are Egyptian blue is closely related to Chinese blue chemically, and also as a use, because it are two pigments. But there is also some other pigments like Egyptian green that is closely related for the production technique, and also chemically, but there is a different structure, very different structure. And there are also other problems, for instance, the color that change with granulometry, so with the dimension of the particles. So all these aspects should be treated in an exhaustive way, not just with some hint somewhere, but you, as a researcher, need to have a place to find information on these topics. The unsolved debate on nomenclature, what is? For all this presentation, I use the Chinese blue and Chinese purple definition of those two pigments, and this is because those pigments were invented long before the Han Dynasty, and so many authors that studied Chinese blue and Chinese purple, especially in a recent year, proposed this move in this new way to call them, and that is more appropriate, because if not, it's like we call maybe some Egyptian blue found in Egypt, that we call it Roman or blue. No, it's not. It's very misleading, I think. And so I choose to to follow the new line proposed by many authors in recent years and call them Chinese blue and Chinese purple. That one, but there are another also problem in nomenclature that is blue frit. The term frit is misleading because there are many different ideas on what it means, the term frit, and so I avoid to use it for my presentation, and I suggest to move all in the direction of calling it simply Egyptian blue and Chinese blue and Han purple, and Chinese purple, sorry. The structure, so there are many materials that are strictly correlated to Egyptian blue structurally. One is Chinese blue, but is not the only one. There is gillespite, for instance, and there is also the Westelsite, that is the one, the kind of Egyptian blue that has strontium instead of calcium. And there is also some, probably with gillespite group member like the one with the barium and magnesium tetrasilicates. So all those materials should be treated together to have better in mind their relationship, structural relationship. And also Chinese purple has a similar structure and should be put in a right relationship with the other kind of material. This is an incredible, I think, image that Admir Masic took in Museo Egizio in Turin. And so the relationship about the technique of production. So we have faience and Egyptian blue that have almost the same raw materials, and there are many links between them in the production technology. We should focus, I think, a lot on studying the relationship between those two materials. And as we can see, to recognize them just by color is very difficult. And also, strangely, in the same net, we have some beds that is made of Egyptian blue and some beds that is made of Egyptian faience. And it's incredible to think that why? There is some intention in the bottom image, but it seems not intentionally in the middle image. So study better all those things that stay on that field is I think very important. This image is known, but just to say the data update is straightforward. We need to have that update because we have in those 25 years, but also in the last 10 years, we had a lot of new information that should be a standard. It's very misleading when you read a new paper that states again that Egyptian blue was invented in the 3rd millennium BC and not in the 4th. And we have new information, and I think that everyone should use the most updated information if possible. Chinese blue, already I've said, that it was born far before the Han Dynasty. That is, Han Dynasty is in the 3rd century before Christ, and we have Chinese purple in the 8th century before Christ. So it's a lot of time. So it's the double of the time of the duration of Han Dynasty. So it's really, I think it's really misleading. And so we have other incredible news. This image was shown many times today. So we now have powerful tools to detect the pigments on statues. So we should be aware of that. It should be a place where we can find information on that. We have other incredible new things that have been happening in those recent years, like the first discovery of evidence of production in Italy of Egyptian blue. Until 7 years ago was kind of a belief. Now it's an evidence. Things change, and we should accord to those new data. And another very, very important discovery is that in Italy we produce Egyptian green, not only Egyptian blue, but in Cuma it was found a workshop that produced Egyptian green, and we have very few evidence of the use of Egyptian green in Roman times. So I think that a direction, for instance, for archaeometry on Roman pigments is to search for this Egyptian green. It should be present somewhere if they produce it in Kuma. And so I expect in the next future to have some evidence of the use of Egyptian green and a better way to identify Egyptian green on Roman plasters and frescoes. And we have to say that this turned to be the El Dorado of Egyptian blue production. So we have 4 cities with the sign of production of large facility for production of Egyptian blue. This is really a turning point. This is an image of Giacomo that showed this evening. This is another very incredible possibility now to detect very easily this kind of mosaics that if you look carefully, you can see that are only produced between the 1st century before Christ and the 1st century AD, okay? So just 2 centuries, and all were in nymphaeums or fountains, so close to the water. Why? We have an answer in a while, so follow the things, but we go and move to another point that is very important. So the decrease of production of Egyptian blue during Middle Ages. I think that it should be now accepted by anyone that there is no the abandon of Egyptian blue during Middle Ages, but just a drop in use. So it is a continuity of use. We found in each century some example of the use of Egyptian blue. So it never stopped the production of Egyptian blue, simply decreased for some reason. We can have hypotheses about that, but it should be assumed that it's not that there is a single situation, but there is a number of new finding of Egyptian blue. And I think that this is another data that should be accepted by everyone. The use in Renaissance, that is not something that is just a spot, but we have 4 cases now. Until 12 years ago, we have 0 cases. So, 1 case, to be honest, the Baraldi one, but that they found in a plaster in Bologna that is not here, but it's the 5th evidence of Egyptian blue in Renaissance. But now we have a lot of new information that should be implemented in new papers. Obviously, there is also the Raffaello one. That the turning point here is that it brings to the birth of Bluenet. So this is the good news. There are also reports of new hypotheses and theories. So why this production, for instance, in Renaissance? So is something that was found maybe in excavation, and so they take the pellets of Egyptian blue they found, or maybe some blue tesserae from an nymphaeum and grind them and produce Egyptian blue and use it, or they found a way in Vitruvius because they were highly involved. Raphael was really close involved with Vitruvius in its translation. He commissioned the first translation of Vitruvius in Italian in 1514 year. And so just two years after the production of the Galatea fresco. So it's very close. He was a close friend of Fra Giocondo that in 1511 made the first edition of Vitruvius with illustration. So they were close friends. So it's not impossible that they have a knowledge about the new, that at the time new recipe of Vitruvius. I don't know the answer, obviously, but I think that research can focus on this. Other theories are the also Maurizio expressed a lot of this, so I don't go again on it. But this shortage of natron is a very interesting matter. So we know that the glass production go in trouble between the 7th and the 9th century, and we observe that Egyptian blue production is at the same in trouble on that times. So it's there a link between those situation, because they both need the natron, and so that could be a focus. And there is maybe also other reasons, so to use zinc or whatsoever to try to face this shortage. And another important thing is that we should face controversial issues. We have a big one that was never said today, strangely, or almost never, that is chromatic alteration. Chromatic alteration still is a matter of debate, because even if we take if we take the green alteration or the black alteration of Egyptian blue, both of them are controversial. So the green alteration could be because there is copper chloride cancer that produce copper chloride, the bronze cancer, and so a kind of chloride-rich environment that promotes the formation of copper chloride. And this is a theory, and there are many papers on this topic, so probably it happened. But we know also that copper chloride has been used as a pigment, and there are some evidence of this also recent. And so it's a debate that should be still go on, and should be better understood, probably, the mechanics that stay behind the transformation of Egyptian blue into copper chloride. There are other possible reasons why we can see green Egyptian blue. For instance, the yellowing of varnishes, the mixing with other material, the partial production of Egyptian green, with many theories, but I think that they should be faced better in new line of research. Also for the blackening, there is the same problem. There are theories. The first one was that some copper oxide forms, but in 2004, a very good paper by Daniels clearly states there is no copper oxide and this is black. So why it is black? This is not still very well understood, I think. So I think that we should focus on this also because our topics that are fundamental for the conservation of material that has Egyptian blue inside. We also have not to forget new ideas. So exfoliation happen also in archeological objects. So the natural exfoliation, what brings to our pigments? This could be a problem. So we should maybe avoid the transformation, the exfoliation, unwanted exfoliation on archeological objects. So probably we should better understood these topics. But the last two slides are about the new features that have completely changed and deeply changed the world of Egyptian blue. The first is the discovery of its great biological effects that we don't take into account. For instance, coming back to the nymphiums thing, so about why it is used just where it is water, maybe because it is a very effective algal inhibitor. So I use that intentionally in a place where I want to avoid the formation of algae. Could be an idea, for instance. We don't know if they were aware of this, but it could be an interesting hypothesis. Or Pliny states quite clearly in book 33 of Naturalis Historia that Egyptian blue was used to heal the ulcers on the skin. Why? Because there is the angiogenic effect, the antibacteric effect. It disinfects and promotes the formation of new tissue. We know that. We now know that. But we have to take into account if in the ancient time they know that. And also we have instead to fix some errors that are in literature, like the one of the blue bread that was expressed by Wiedemann and Berg in 2000, in the year 2000. They state that maybe Egyptian blue was used like a preservative for bread, but we have fixed this because we have checked for the original translation, and we have detected that probably was an error in translation between cake of Egyptian blue and bread of Egyptian blue, and was another meaning. Okay, so it's important also for the review this. And for last two slides. Okay, the photoluminescence is something we know, but the important things are those three emerging aspects. So excitation using UV and NIR. This is a very, very important point for the archaeometric community. Why? Because UV is absorbed very quickly and very effectively. So we can promote a better luminosity, a better photoluminescence using UV light in specific condition. Maybe, but we have to search for that. And another important thing is that we can use near infrared light. That is the approach that is of biophotonics. So why? Because maybe we want to sketch, to sketch the hidden Egyptian blue. So if we have Egyptian blue behind a repainting or behind a layer of dust of something, we can see it because we use a wavelength that is penetrating, that does not stay on the surface but go beyond, and let me possible to see Egyptian blue. So also new method need new check.
Please.
Color is widely accepted and finished, and part B is coming. So any suggestion?
We have voices from Bluenet that we need to leave some space to. I'm happy to close this session with a theme that definitely is close to my heart. So I thank you all to contribute for new perspectives of using this extraordinary pigment. So voices are the next. Un minuto di pausa? No. Ci ho provato,
No, grazie. So, good evening. Okay, good evening. It's an honor for me to be the chair of the last session of this meeting. And in order to not to waste time, as the schedule is very tight, I will introduce immediately the speakers and asking them please to keep in your 10 minutes time in order to conclude the meeting in time. Thank you very much. So now we have Giovanni Cavallo from Scuola Universitaria Professionale della Svizzera Italiana, Lugano, who will tell us about Egyptian blue in Carolingian wall paintings, preliminary scientific data, and future perspectives. And he should be connected through Zoom. So.
Okay. Can you hear me, please?
Yes, it's a bit too loud. Just a moment, we are fixing the audio. Can you try again?
Yes, can you hear me well?
Perfect, thank you.
Okay, thank you very much for the introduction. And thank you very much for this very nice opportunity to be there and to share the preliminary data concerning our research on Carolingian wall paintings and particularly in this case on the Egyptian blue. This research is part of a wider project funded by the Swiss National Science Foundation, Forgotten Colors, rediscovering the original polychromy of early medieval wall paintings in the Raetia Coriensis region, with the scope to reconstruct the entire process of wall painting execution in several sites between Switzerland, particularly in the southeastern part of the nation, and in the northern part of Italy, corresponding to South Tyrol. So there are many institutions and people involved in this project, because there are many questions, and so some specific issues are discussed and by partner universities both in Switzerland and in Italy. So we are working on these sites from point 1 to 7. They are located in this area called Regia Curensis. And the basic idea is to analyze the wall paintings here and also to make correlation with other sites in northern Italy and in other part of Italy. That is in this slide we have some pictures where some very nice examples of well-preserved wall paintings have been reported, and in some cases there is also the availability of painted fragments. Here, for instance, in the monastery church in Byzantium, we have just plastered painted fragments. So the research question, what materials and techniques were used for the creation of early medieval wall paintings? And another aspect is related with the provenance of raw materials and with the technological process related with the production of artificial pigments, and how do the identified characteristics compare to each other and coeval data, and what does this tell us about the organization and ramification of artistic projects in the area of interest, and also aspects related with the deterioration of wall paintings and pigments will be discussed in this project. So in terms of methodology, the application of non-invasive analysis has been proposed. We are working on using non-invasive analysis in the first year of the project, and after that we will move to macro sampling for the reconstruction of microstratigraphy and for studying the chemical composition and the microstructural features of the pigments, and after that more in-depth analysis will be used, in particular laser ablation for trace elements determination and isotope analysis for provenance studies. Well, some examples that we have at this moment. This first example is from the church, from the crypt of Saint Stephen in Chur, where there is evidence of the presence of Egyptian blue on some small areas corresponding to the upper part of the east wall, and also on fragments there is the evidence of Egyptian blue and associated with green lines of green earth. And what is important to say here that is that there is the presence of zinc associated with copper, and maybe this can be an indication of the use of brass as source for copper, as highlighted earlier by Maurizio Ceto in his presentation. Naturally, these are very, very preliminary data, and so more discussion is needed to demonstrate this evidence. So in this monastery, where only painted fragments are available, there is not any evidence of blue pigment, and so there is not any evidence of the presence of Egyptian blue. So most probably here the blue tone of large surfaces was realized using carbon black mixed with lime. And evidence of Egyptian blue was found in the Holy Cross Chapel in Mustire, in this detail of a figurative scene in the north wall of the nave, and also the use of the same pigment was found for delineating some details of the tunic of this figure in the convent church. And it was also found on painted fragments. Later on, another site is St. Peter Mishtal in Albaschein. And here, for some reasons linked to the logistic situation, the analyses were carried out by the University of Nottingham using hyperspectral imaging. So the results will be available maybe at the beginning of the next year. What we know now is that analyzing painted fragments, we didn't find any evidence of Egyptian blue. Also for the fact that just yellow and the red ochre was used for decorating these fragments. And we moved to the Italian part of the project in San Benedict, where the pigment was used for the figurative scene, and also for some part of the drape of Christ in this image. And in San Proculus in nature, there is also the evidence of this pigment, and the campaign will be done soon to consider also other surfaces that have not been analyzed until now. So these are some concluding remarks. These are well-known things to the Bluenet community, that non-invasive analysis such as VLXRF and FORCE allowed for the identification of the presence of Egyptian blue in all the investigated sites, with the exception of Vicentis Monastery, where no blue and also green pigments were detected. And this data will be compared in the Raetia Curensis region and also with other relevant sites mentioned earlier, because we have evidence of the fact that, for instance, in San Saba in Rome, Egyptian blue was mixed with natural ultramarine, and copper comes from a pure source. In San Clemente in Rome, we have evidence of the low level of crystallinity of Egyptian blue, and there is also the presence of a huge quantity of quartz, indicating a low level of manufacture of the pigment in San Vincenzo al Volturno. The copper was from metal alloys such as bronze, and in Castelsepro we have already heard the use of copper from brass as possible source. Data are extremely important for planning and
I must ask you to sum up as time is up.
Yes.
Thank you.
Yes. Just a couple of slides and we'll be concluding.
No, I think we don't. I'm afraid we don't have no time. I'm sorry.
Okay. So, thank you very much for this great opportunity.
Thank you to you, and for coming here. Okay. And now I'm calling Luca Villa from the Foundation Pro Convent of St. John, Münster, Switzerland, with the role of Egyptian blue in early medieval wall paintings, insights from the cases of Münster, Valmünster, Switzerland, and Malles in Val Venosta, Italy. Is he connected? Yes? Okay. So, you're welcome.
Hello, everybody. Could you hear me?
Yes.
Yeah, okay. Greetings to all from Münster, and thank you for the invitation to attend the conference. We are sorry to be not here with you in Rome. Tomorrow we start the new analysis in San Proclo a Turno, and for this reason we are in Münster now. The contribution that I am going to present has been realized in close collaboration with Patrick Cassiti as part of the Forgotten Colors project, which Giovanni Cavallo has just told us about. The focus of our presentation concerns the use of Egyptian blue pigment in some early medieval painting cycles from the Carolingian era, starting with the example offered by the revision of existing data and the new investigation carried out in the Church of St. John and St. Cross in Münster and in the small chapel of St. Benedict in Mals. The data collected until now will have to be considered and processed even more carefully. However, it's already possible to offer some reflection or guideline for research, also by comparing these cases with what is already known about the use of this pigment in the fresco of the period. In particular, the suggestion offered by the well-known example of San Saba, San Clemente, Santa Maria Antiqua in Rome, San Vincenzo al Volturno, Santa Maria Foris Porta in Castelsequio. A first question concerns certain aspects of chronology and in particular the possibility of defining a sort of link between the use of Egyptian blue in the fresco in the Roman period and this attestation in the early medieval ages, when seems to have had a great development in Italy and the Alpine area, precisely from the late Longobards time and above all in the Carolingian period between the 8th and 9th centuries. About chronology, are of particular interest the evidence of Egyptian blue at two sites in the Alpine area. At St. Peter of Grash, near Meran in South Tyrol, recent analysis have tested the presence of this pigment on erratic fragments of fresco found in the level below the floor of the early medieval church, dated between the 8th and 9th centuries. They may belong to earlier phases of the building that can be dated between the 5th and 6th centuries. However, there are no further indication of the use of Egyptian blue in this case. Its presence nevertheless appears significant. More interesting is the evidence of Egyptian blue in the fresco of St. Stephen's in Chur, as investigation has shown. Here it is possible to identify the pigment in the paintings on the eastern wall of the first building, which was built as a bishop mausoleum, probably between the late 5th and the early 6th century. On this wall, in two areas of the fresco still in situ, IR images show typical luminescence stimulated by VIL. In one case is the background, perhaps of halo of the sky around the head of some figures of apostles or saints. In the other case, details that would seem to define architectural structures. It is difficult to say if it is an original painting or a later refinement. They would seem superficial layers probably given with the lime glaze. In fact, Egyptian blue was certainly used in the second decorative phases of the complex, which can be dated to the 6th century, as is documented both in the finding of pigment in a fresco in situ beside the central niche of the wall, and in some erratic fragments in the archeological excavation. Then, it's now possible to enrich the panorama of attestation of the use of Egyptian blue after the late Antiquity period by adding the case of Church of San Stefan to the 6th century example of Santa Maria Antiqua, first level of the palimpsest with Mary Queen depicted on a blue background behind the throne. I have to thank you to Valeria Valentini for the information. Later, the first century evidence concerned the wall paintings of the Church of San Saba in Rome, dating back to the first half of the 8th century. Here, Egyptian blue and lapis lazuli were detected mixed together in the same pictorial layer, as we shall also see in Mustire and Mars. There are the oldest Western painting in which lapis lazuli was used as a blue pigment. There are still now a lack for the use in the fresco during the 7th century, but we have no fresco from this era. Mustire, let us not consider the situation of St. John, a monastic church erected in the last quarter of the 8th century. The painting dates from the early Carolingian period, shortly after the church was built. Extensive use of Egyptian blue emerged in the fresco of the church. In one case, however, on the east wall, with Christ and a mandora flanked by angels, the use of both Egyptian blue and lapis lazuli is attested. The images with IR fluorescence confirm the presence of Egyptian blue, and in the shadows of the robe, analysis indicate the presence of Egyptian blue and lapis lazuli used together. Also confirmed by the section of sample taken from this area. In this case, the Egyptian blue is probably related to the rare grains or smaller grains mixed with lapis lazuli used as primary pigment. In the same scene is therefore testified the use of two different shades of blue obtained with two different pigments were then applied side by side. Lapis lazuli was used for the blue background and also for the halo of Christ. The Egyptian blue are in the face shadow, halo and wing of the angel in the mandala back of Christ. In the angel's halo, there is a dense layer of the Egyptian blue. Extensive use of this pigment is documented in other fresco. You can see the images. The sky background with blue pigment show a dense layer of Egyptian blue confirmed by a thin section of a sample. In some cases, the Egyptian blue was used to obtain a green tone over a layer of ochre or mixed with ochre. Another example of this situation is offered by scene 17, as we quickly see. There is an extensive use of Egyptian blue. You can see the large use of the pigment to define the details of the robe and the sword. In this application of Egyptian blue for the background, less intense drafting of Egyptian blue for the morphological details of the figures. In fact, you can see a less intense IR luminescence. Egyptian blue is overlaid or mixed with other pigment, ochre, maybe to create a green color. Other cases show a use of Egyptian blue in connection with the creation of a green tone. In particular, appears mixed of overlaid with ochre for the background green of the tondo with mask. This is also confirmed by the thin section of a sample. To resume, in Mustile there are extensive use of Egyptian blue, a dense application for the background for the yellow, a use to define some morphological details of the figures, a use to highlight morphological details of faces, in particular shadow, sometimes with a less dense drafting, overlaid or mixed with other pigment to create the appearance of brick green color. Also, sometimes used in this way for the background. A use with lapis lazuli to obtain two different shades of blue applied side by side. Only in some cases, it is for dress shadow, it is used overlapped or mixed with lapis lazuli. Always in Holy Cross Chapel, we have the present of Egyptian blue. Giovanni told that show us images, this is images that represent the crown and the area around the figure in which we are the use of Egyptian blue for the particular. Let us now look at slightly different situation concerning the Church of St. Benedict in Mars, a patronal chapel erected and decorated in the Carolingian period between the late 8th and the early 9th century. The evidence of Egyptian blue concern only the fresco on the east wall.
Sorry, I must ask you to sum up as time is up. Just a few.
Allora, in summary, for what we got Mars, the first analysis hardly reads the presence of Egyptian blue in the Mars fresco. In the blue backgrounds or gray-blue shadow and superficial white glaze. Force show the prevalent presence of lapis lazuli, but with a non-pure spectrum, which predicts the presence of another component, compatible with Egyptian blue. XRF analysis reads the presence of copper pigment at the point where lapis lazuli is witnessed. Multispectral image confirms the presence of Egyptian blue and lapis lazuli with a striking overlap between them. Probably a significant sign that they have been applied together.
We have to close now. I'm sorry because we are really up with time. So I thank you very much for the presentation. Thank you, and thank you. And I call here Giulia De Vivo from Rijksmuseum Amsterdam, the Netherlands, with some new results on Garofalo's use of Egyptian blue in the Rijksmuseum Adorazione dei Magi.
Buon pomeriggio, good afternoon. Thank you for this kind invitation to be present today. My presentation is a joint effort, research conducted with my colleagues Francesca Gabrielli and Annelies van Loon, both research scientists at the Rijksmuseum, where I'm a painting conservator. I will talk about the Adoration of the Magi, a painting by Benvenuto Tisi da Garofalo, a rather small panel, circa 80 by 60 centimeters, that is part of the Italian collection in the Rijksmuseum. The entire collection, which counts more or less 200 paintings, is ongoing a research project, and the end product of the research will be a new technical catalogue. So the research starts with close examination of the painting and the painted surface with stereo microscope and a set of imaging analysis, non-destructive, well established, like presented here on the screenshot. This protocol is applied as a standard on all the paintings, and the information gathered is then discussed in a joint meeting in front of the object by the conservator and the curator, and this is always a very fruitful exchange. Some paintings of the 200 are selected for a second research phase, which is designed ad hoc to answer specific questions. The Garofalo immediately stood out as an interesting case for both technical and art historical reasons. Despite being a subject that he reproduced many times through his oeuvre, he was always searching for a slightly different composition, and in our panel there's a very tormented underdrawing with some features positioned 4 or 5 times. With the research conducted so far, we could not make sense of all these changes that continued in the painted phase, and especially I want to point at this line here, this fold, which was discarded in the final composition and that follows an underdrawing line. This sprang our enthusiasm, and we decided to take the research further, looking at in-house available techniques such as macro X-ray fluorescence. This technique delivers chemical elemental distribution maps, but still we could not make sense of all the pentimenti occurred. The copper map, for example, can relate to various copper-containing blue or green pigments, as we all know, and so we saw that there is some blue pigment here, but we could not make sense of the entire evolution, compositional evolution. By the time we were studying the Garofalo, we were so lucky to have the presence of Professor Nakai and his research team from Tokyo University of Science in the Rijksmuseum taking some measurements, and so we could put the Garofalo in front of their instruments, and immediately both UV-vis spectrometry and X-ray diffractometry pointed out to the presence of Egyptian blue, which was quite surprising for us. So we decided to confirm this finding, and that this was one of those cases where we would leave non-destructive to take a sample and confirm it. And the sample showed that there were at least 4 layers of blue, and Egyptian blue was found in a mixture with ultramarine in the 3rd layer from the bottom, on top of the white imprimitura that you do see here. So the layer containing Egyptian blue is the one up there, and you see the co-presence of 2 different pigments which have different color and shape in the grains. We could, thanks to SemiDX, confirm the presence of copper, silica, and calcium in a single grain, and hence confirm the presence of Egyptian blue. And thanks to SemiDX, this is also very clear that there are some elements associated with one pigment and some with the other. So we turn to VIL, like Egyptian blue scholars do, to visualize the spatial distribution and the use of the pigment. And another little discovery was that it was not confined to the main figure of the Virgin and the main compositional group, but also for minor details in the background, like, for example, the shoal of this figure there on the far right. So, of course, we dove into literature and found that there were other 2 Cinquecento Ferrarese examples already published. And so with our Garofalo, this makes a nice group of paintings that are linked somehow for geographical and date. And the one in the National Gallery is from Garofalo again. As we all know, it was also found later in Raffaello, which predates the occurrences of the Ferrarese paintings, and there was new research input. We were very grateful to be invited to be part of Bluenet. So we decided that this was the good time to ask the painting to come back to the Conservation and Science Department of the Atelier building in Amsterdam. It's usually, unfortunately, in storage. And this was a good time, not just because we were part of Bluenet, but because by this year the museum had acquired new analytical technique, so we could do a new study campaign. And we started with reflected imaging spectroscopy, which is a technique that collects light which is reflected or scattered by the elements composing the paint layers, and the outcome is a huge data cube that can be sourced for information, and the data cube has X and Y dimensions relating to the dimensions of your painting, and the third dimension relates to the spectral wavelength band collected, but it's a technique of spectroscopy, so we can also source a single pixel, get the spectrum and map it to through the surface of the entire painting. The data cube can also be sliced and at different wavelength, and getting 3 of them and combining them in a false color infrared was quite useful. In the 2 details, I hope you can appreciate the underdrawing that we were discussing before, very visible and very tormented freehand underdrawing in a liquid medium. And so we could nicely, with reflected imaging spectroscopy, visualize the presence of the underlayer of azurite, for example, and this matched the information we had from the sample, that azurite is present in the underlayer, in the 2 underlayers. So this and here mixed with lead white and some red lake. But we tried also to map some spectral features typical of ultramarine and Egyptian blue. For Egyptian blue, we looked at the reference spectra and could single out this absorbance at 800 nanometers. And we can compare the 2 maps thus obtained and see that they map the same dark blue elements in the composition, but they don't match completely, meaning that we are indeed imaging different elements. And the 2 differences can be easily interpreted with presence of little damages or over retouches. Since we had the camera, the spectroscopy camera, the painting, and the setup and the time, we decided to try and acquire luminescence imaging spectroscopy. So we tweaked our setup a little bit, and we could obtain a clear luminescence spectra centered at 900 and map it on the surface. This technique has also a very high resolution, so we could zoom in and see some details that we had missed in VIL that we did before, like these 2 horizontal strikes. I'm a painting conservator, so I went back to the object and looked at it with a stereo microscope to try and see what we're exactly mapping. We tried photomicrograph with VIL. The setup needs improvement, definitely, but we still could obtain quite interesting photomicrograph in VIL. And going back to those horizontal brushstrokes that were puzzling us, and here I conclude, they relate to highlights in the white steppe, and that match very well with his technique. But just to conclude, we have new data, we have to source it better, but we still are not really further in answering our open research question, where the Egyptian blue came from, and was its use intentional or not. And with this, I thank you very much for your attention.
Thank you very much. Thank you very much to Giulia. And now I'm calling Lorenzo Giuntini, INFN Florence, which will tell us about Machina, the first movable accelerator for cultural heritage in situ applications. Please.
Good afternoon, everybody. And let me thank the organizers and especially Antonio for this kind invitation and the opportunity of presenting here our work in this fascinating place, and something that pushed me to say something like delenda Carthaginem, but this time it's better not to say delenda, maybe something different. And I will start with a short summary about IBA technique, which are a way to characterize in non-destructive and non-invasive way samples, in particular samples of interest of cultural heritage, and they allow for point and imaging characterization, and provide pieces of information of interest for many different kind history, art history, technology history, and many other fields. So over the time, this IBA technique have been used for providing and characterizing objects in cultural heritage in hundreds of applications dealing with many different artworks, for example, metal statue, porcelains, or gold jewels, or glasses, for example. They helped, this very nice example, were used to recover the lost images in a glass-stained window in the Rosslyn Chapel in Scotland, and also interesting comparison between IBA results and XRF, which is possibly more known in this community, showing that IBA can be somehow more appealing when dealing with low Z elements. And they have, of course, been used also to study Egyptian blue artworks. So, being so interesting, they have produced hundreds of applications, and one question arises in quite a natural way: why only hundreds of applications, being these techniques so appealing? And the answer is quite easy, because they need an accelerator particle, that means MEV particle produced by a particle accelerator, which means that you have to bring the sample to the accelerator laboratory. And most often, cultural heritage samples cannot be moved for many different reasons, either because they are unmovable as frescoes, or because they are too fragile, or the transportation is too expensive. So this means that the number of applications is intrinsically limited. So if we cannot take the artworks to the accelerator laboratory, naturally one asks himself, maybe I can do the opposite. And of course, this is an impossible mission, as typically you have hundreds of tons of instrumentation, kilometers of cables, and so on, big absorbed powers. So this is a challenge that we have taken with the Machina project, a common INFN, a National Institute of Nuclear Physics, and CERN project. The idea is to provide something that is a transportable system based on a particle accelerator, which is able to provide us with an MEV proton beam for standard IBA measurements, with some very heavy constraints, that is low power consumption, low weight, small form factor, very small form factor, low cost, and of course a transportable system. So just a few hints of the system. We started with a traditional source, a radio frequency source, which has been almost completely dismounted and reassembled in order to have a very simple, reliable, efficient, no power consuming system, and no liquid cooling requiring. So it has been completely redesigned, and this is how it looks like. That some parts are still the original, but all the others have been changed. How this is the connection of the control panel with the power supply needed for creating the plasma, and so creating the beam. And this is the source switched on, and it's nice bright pink color. This is the accelerator, the first image we got for the accelerating cavities. Just to squeeze to the essential, they are 1 meter long as a whole, and have a 100 kilogram mass together. And they need just less than 6 kilowatts, roughly, or kilovolt ampere, depending on factors. However, very small power. That is, this power is available even for house delivering. In some houses, it's possible to have such a power. nothing comparable with the power required for normal accelerator systems. So this is the high energy, what is called a high energy beam transfer line, a pipe with 2 permanent quadrupole magnets, which means again we don't need power provided by power supplies, electrical power supplies, so we cut down weight and also the need of cooling. This is how the whole system looks like. See, 3-section, source, acceleration, and underneath the control electronics, and the final part where the beam is focused and extracted into air. This is a picture of how it looks like with all the system connected, also the power supply and the cooling system for the cavities. And this is a comparison between our standard accelerator we have in Florence for IBA analysis. It makes also radiocarbon dating, but it doesn't change too much. And the comparison, I think, it's quite apparent, the success of the Machina project. And also, that system is transportable. We have been going back and forth between Florence and Geneva many times, 6,000 kilometers. And the structure we prepared proved to be quite efficient, easy to use, and vibration free. Oops, sorry, I would like to show. You see, if you have a look at the accelerator, you see that it doesn't move, even though everything around moves. And so this is the first extracted beam. It has been produced this summer, and we have something below the millimeter size, so able to provide a probe which is suitable for characterization in the cultural heritage field. And I can conclude saying that we are now testing the detection system, that the system will be able to provide a compositional imaging, and that we are going to test the system in Florence. Those results have been obtained in Geneva at CERN, and that the Machina, the second project, the Machina 2 project, is on starting, let's say so. We are discussing the very beginning of the possible Machina 2. That's all. Thank you for your attention.
Thank you very much for your relation. And I'm now calling Joanna Caculli from the University of California, Los Angeles, with probing nanoscale heterogeneities in Egyptian blue through scanning, transmission, electron microscopy, and synchrotron-based X-ray spectrum microscopy. And she should be in Zoom. Yes, good evening.
Hello, good afternoon, everybody. Can you hear me well?
Yes. Can you hear?
All right. So, yeah, I can hear you. So it's really wonderful to be here with you today, even remotely. I wish I could be there in person, alas, that was not possible, too much teaching. So la prossima volta spero. Well, Antonio and everybody else who has worked really hard to make this happen, to bring all of us together, thank you really very much for this opportunity to learn and to share. And so far, this has been really an amazing meeting with very, very interesting presentations. So just a few words about our research group at the University of California, Los Angeles. We focus really on 5 scientific pursuits, all related to ancient materials and technology. I'm not going to go through them in detail because of time, but we really focus on archeological forensics. We are expert consultants for Homeland Security and the FBI. We, of course, work on ancient technology through reverse engineering to understand technological processes and the chemistry of materials. We also work on human agency and the environment to understand paleopathologies and how people really interacted with the environment. And also quite similar to what Admir and Professor Selvaggio and Nicola said, we also work on archaeo-inspired materials for the development of novel materials. Here you see some 1D nanoscrolls inspired by Chinese blue. And then finally, we also work on biocultural diversity and conservation with the synthesis of sustainable materials for ecological and cultural preservation in a more integrated fashion. And with this very short intro to my group, I would like to start my talk that it really focuses on the production technology of Egyptian blue. So listening to the amazing talks today, however, it is interesting to reflect from the first time since scientists got interested in this ancient pigment and following decades and decades of exploration of Egyptian blue, historically, archeologically, but most importantly, scientifically, we are here today in 2022 discussing Egyptian blue. Don't you think this is really fascinating? It could be a bit perhaps crazy, but I'm going to stick to the fascinating part. Well, here we are. Egyptian blue never got out of fashion and never really stopped attracting the attention of scientists and scholars. So given that I'm presenting this almost at the end of the meeting, I would like to summarize a few key points about this pigment's production and the importance of advanced technology with improved lateral resolution for the analysis of pigments like Egyptian blue, characterized by a highly microheterogeneous structure. I believe we would all agree that the synthesis of Egyptian blue represents a significant technological achievement, and not only, considering also the social relations through which human labor has used to transform raw materials into this pigment. After all, its manufacture culminates from emerging craft productions and adaptations from advancements in various ancient industries, primarily those using heat treatment, notably metallurgy and glassmaking. From a materials perspective, Egyptian blue is considered a high-tech sintered quartz ceramic, as many colleagues also mentioned earlier today. It represents a notable example of a synthetic high-fired sintered polycrystalline material known as frit with three major phases. A crystalline phase containing this layered square planar copper cuprate, also the isostructural part with Chinese blue, unreacted quartz and glass. You can see in these images here the three main phases in Hellenistic Egyptian blue and its contemporary hand blue. Besides these major phases, this highly heterogeneous pigment also consists of other crystalline and amorphous phases, which are associated with the pigment's production. This often at submicron level, they could be byproducts or precipitates, result mainly from the excess of silica, calcium, and copper oxides and excess of alkalis that were used as raw materials. These are very important, and this is what is emphasized in my talk today, as they could hold the key to a series of interconnected processes on the pigment's production technology and also materials variability. Our knowledge on the production technology of Egyptian blue is based primarily on direct analysis of raw pigment pellets or pigments already used in paint layers, combined with ancient primary texts, historical records, as well as laboratory experimentation to recreate the pigment. So this integrated methodology aims at decoding the conditions for its production, like the heat treatment, and gaining an insight into the type of raw materials employed for the synthesis, the ratio of materials, and the step-by-step processes for the pigment's production. Based on the data obtained from such previous studies, possible raw materials include beach sand or quartz pebbles, malachite, azurite, or smelted copper, limestone or calcium-rich sands, and natron as the flux to lower the melting temperature of silica. Also, we know from reverse engineering and experimentation that in order to sinter it into a dark blue solid, these raw materials must have a molar ratio of calcium oxide, copper oxide to silica of 1:1:4 and fired between 800 and 1000 degrees Celsius at oxidizing conditions. Traditionally, scanning electron microscopy and microprobe analysis assisted in the classification of Egyptian blue pigment based principally on the characterization of the major phases. These two backscatter electron images of samples of Egyptian blue from Switzerland and Greece respectively show the major crystalline phases of Egyptian blue, unreacted quartz, and interstitial glass. What is different in these samples is the composition of the glass phase, which varies according to the fluxes used. The sample to the left, dated to the Roman period, contains a soda-lined glass, where the other one to the right of the Hellenistic period contains leaded glass. To our knowledge, lead was only identified so far in Hellenistic Egyptian blue samples. Another example other than the one presented here is from Memphis in Egypt. Being not so common, the presence of lead in Egyptian blue raised questions on the source of copper and or fluxes used, and then it required more investigation. So to improve detection and to address the issue of microheterogeneities in Egyptian blue, Our samples were further analyzed using synchrotron-based X-ray spectroscopies. The elemental maps we see here of two Hellenistic Egyptian blue pigment samples from Delos in Greece show the abundance of spatial distribution of lead, corroborating previous data on the use of lead compound as one of the raw materials used for the production of the pigment. While XRF alone was not able to provide additional information on the origin of the lead, the detection and identification of tin at the concentration of 0.8 weight% raised additional questions on the nature of the chosen raw materials. To answer these questions, scanning transmission electron microscopy was used. This has helped us take things one step further, as it enabled us to visualize and identify both crystalline and amorphous phases at the nanoscale and complement results from the SEM and synchrotron analysis. So to analyze samples with the STM, we first used focused ion beam on a polished cross-section of Egyptian blue to slice an ultra-thin section across areas of interest. To the left and center images, you see the areas sampled with the FIB cuts marked with red rectangles, and to the right, you see one of the ultra-thin slices taken by FIB that includes the different crystalline and amorphous phases. So using STM, we were able to visualize and verify the crystal structure of Egyptian blue and also identify other byproducts resulting from the processing of the pigment. To the left here, you can see an atomic resolution STM image of blue single crystal in the 100 orientation, showing the ordered crystalline structure characteristic of the calcium copper tetrasilicate phase. By indexing the diffraction pattern with fast Fourier transform, we were able to measure the lattice parameters, which were very close to the reference values we get for natural mineral cuprorivate. To the right, the two-beam condition shows the presence of defects in the single crystal and the presence of calcium silicate and amorphous silica. Further analysis with STM EDS focused on other submicron amorphous and crystalline phases found in the defects of Egyptian blue. Here you can see maps of element abundances corresponding to the high angular dark field image that you see on the left. Results from this specially resolved TDS analysis, supported also by diffraction patterns for some of the submicron crystallites, indicated the presence of tin compounds associated with lead and copper, suggesting the reuse of leaded tin bronzes as the source of copper. Based on their molar ratios, this could also be in solid solution that could also inform technological processes and firing conditions. Other submicron scale inclusions identified within the crystal defects or dispersed within the leaded glass phase by means of STM EDS and by indexing diffraction patterns include sodium silicate, lead sulfur-rich phases, as well as sodium sulfate and sodium chloride. So this analysis of high specificity and improved lateral resolution enabled by advanced technology and large-scale facilities helped us refine our understanding on the raw material selection and processes for the manufacture of the pigment. For example, the identification of tin and lead in Hellenistic Egyptian blue samples provides additional clues on the technology and raw material selection, pointing to the reuse of leaded tin bronzes as the source of copper. Similarly, the abundant presence of sodium silicate as a byproduct from the sintering process of Egyptian blue suggests a heat treatment of around 850 degrees Celsius. So it seems while we have conducted so many analyses on Egyptian blue, there is more to learn. The more and the deeper we dig into its structure, while we may get some answers, more questions are raised regarding its technology and production processes. And with this, I would like to end this talk by thanking all of the students and former members of my research group at UCLA, especially Dr. Yuan Li for all her work on this pigment, and my colleagues, Philippe and Gilles from LAMS and CNRS in Paris. I also would like to thank you all for your attention. And if you have any questions, please contact me at the email.
I'm afraid we don't have time as we are closing, but thank you very much for your speech. And last but not least, I'm going to call Roxanne Radpour from the National Gallery of Art, Washington, D.C., with application of luminescence hyperspectral imaging spectroscopy to identify and map Egyptian blue in paintings and polychrome objects. Is she connected? Yes. Can you hear us?
Yes. Can you hear me?
Yes. Thank you.
Great.
Okay.
Wonderful.
Please.
Well, I'm very honored to be wrapping up all these talks. I wish I was there in Rome with all of you because I see a lot of familiar names and new names I wish I got to meet. But so today I want to wrap up by talking about a technique that I've been exploring to identify and map Egyptian blue, and that's luminescence hyperspectral imaging spectroscopy. So we know that there are various non-invasive techniques we want to use or can use to identify Egyptian blue, because non-invasive is our first mode of operation. First and foremost is forensic photography, so using a modified camera with select excitation and capture with filters. If you use optical microscopy, Egyptian blue tends to be, because it's very coarse, and the larger the crystals, the more blue it is. But then spectroscopy techniques such as diffuse reflectance spectroscopy or elemental spectroscopy, we use these signatures to help us identify Egyptian blue in a painting. But sometimes these are not enough, and sometimes we have very challenging situations where using a modified camera or even just using elemental or diffuse reflectance is limiting. So let me give you an example by this wall painting in a tomb in Paphos, Cyprus. And I'm focusing on a green paint on this wall painting. And I'll tell you right now, yes, it does have Egyptian blue. But if I look at the reflectance spectra from fiber optic diffuse reflectance spectroscopy, I can't see the characteristic triplet signature from Egyptian blue. I can only see that it's dominated by green earth, which is the bulk component of this green paint. When I look at the elemental spectra, I do see copper, but that's not enough because we know that there are other ancient pigments with copper in them. So actually how I found out originally that there was Egyptian blue in there potentially was a modified camera. However, just using a modified camera doesn't give me any chemical information. And we know that we're just recording light. We're just recording light from the scene, from the environment. So you cannot say that this light here has a peak at 900 nanometers. And so that's why I'm advocating that we transition to more robust imaging techniques to get us information that's both robust chemically, as well as giving us macro scale information. So let's move beyond the modified camera that only has 3 bands to now a hyperspectral camera with hundreds of bands. And so this is imaging spectroscopy, which is where we collect hundreds of images in narrow spectral bands. And when you stack these images together, you get a 3D data cube. And I think you saw this in a previous talk, an example of this. And most of the time when you hear about imaging spectroscopy, especially in cultural heritage, you think reflectance imaging spectroscopy, or even macro scale XRF. But here, I want to focus on luminescence imaging spectroscopy, where we have these really rich 3D data cubes, and what we're trying to mine out of there with statistical analysis isn't a diffuse reflectance signature, but an emission signature. And so the luminescence pigments that we know are prevalent, let's say in antiquity, for example, are madder lake and Egyptian blue. And we know what their emission profiles look like. So we know how to excite them and then how to record them with filters. And this time we don't want to just record the overall light, we want to record their profile so that we can produce images on where they're located. So now if we look back to that wall painting that I was originally talking about, we brought a hyperspectral camera into the tomb. It's portable. It's relatively low cost compared to conventional hyperspectral systems. And even then, its reflectance spectra could not identify Egyptian blue for me. So still a limiting factor. Again, just for comparison, this was the modified camera photograph that we took. But using a hyperspectral camera and recording the luminescence data and doing statistical analysis to extract potentially a luminescence signature, I record this emission profile, I extract it and I map it, and I get this really beautiful image about where Egyptian blue is located in that painting. So now let's take a look at this painting here. Many of you probably recognize this as a Roman Egyptian mummy portrait. Just by looking at the execution, we know that the artist was very highly skilled. We know the patron was wealthy. We can see a lot of different tones in the painting. This is a painting in the Walters Art Museum collection. We took the hyperspectral camera from the National Gallery of Art to the laboratories at the Walters Art Museum and did luminescence imaging spectroscopy, as well as reflectance. The reflectance data, when we mined the data cube, showed us a bunch of different end members or spectral profiles that comprise the painting. And when we make a map, we see that there are a lot of interesting mixtures, but it seems to be mostly made up of red ochre, yellow ochre, natrigericite. We know from elemental analysis there was lead white, so all of these are mixed together to create the flesh tones. And the green seems to be made of a copper carboxylate, so it's dominant in copper. We know there's copper in the painting. And then there's Madder Lake. But from this data alone, I cannot tell if there's Egyptian blue there. And so again, as we saw before, that's a limiting factor because it is a possibility. We know they're in Roman Egyptian portraits, and if it's mixed finely, we're not going to see it in the reflectance spectra. So with luminescence imaging spectroscopy, we actually took an interesting approach here. Because Madder Lake also luminesces, we decided to excite both of these pigments at the exact same time. And because we're recording luminescence signatures and getting the entire spectral profile, and we know Madder Lake and Egyptian blue luminesce in different spectral ranges, we can record them at the same time and separate them. So we do that by exciting from 430 to 540 nanometers, and then filtering above 540 nanometers to capture both of their emission. So when we collect the data, we have to pre-process the data and correct some of the self-absorption of Madder Lake. We have to then data mine the cubes to find the signatures so we can do chemical mapping. So the end members that I found, or the spectral signatures that dominated the luminescence cube, are stray light, which makes sense. There is, it's hard to get rid of. But then we also have Madder Lake, which I expected because I saw the reflectance profile. And then there was a signature that had background, but it also had a near infrared luminescence bump. And this to me indicated the presence of Egyptian blue. Now, in order to do some creative mapping, I actually corrected this by removing that background peak. And then because all of these signatures together are contributing to the luminescence signal, I performed linear spectral unmixing to produce abundance maps to see how each of them are contributing. So here we can see the effects of the background, but we also now see where Madder Lake is being used, which is much more clearly seen in the earrings and her garment. But now we see the presence of Egyptian blue throughout the tunic and throughout some of the green leaves. And in fact, when we compare it to the photograph taken by the Walters Art Museum, we see that it actually maps the tunic very well. And also it does a better job of mapping Egyptian blue in the green leaves. Now, what we struggled with a little bit was with the face. So I took the data cube and I calculated a second derivative, which takes the luminescence peak and makes it an inverted signature because I really want to access those really subtle signatures. And then I data mined the cube again, and I found two signatures, one that corresponds to most of the tunic and one that corresponds to the face. And if I select out some pixels that we can also see in the digital photograph, we see that inverted peak around 900 nanometers that is corresponding to Egyptian blue. Now, the advantage of working in both reflectance and luminescence modes is that we can compare these data sets together to really understand how the artist is working. So for example, looking at the different green executions on the white tunic, as well as over the pink purple garment, if you look at the reflectance profiles, all we can tell is maybe a difference in intensity, but not really the absorption signatures. Close-ups in the images kind of show a different coloration of these areas. But when we look at the luminescence profiles, we can see a high intensity on the green leaves over the pink purple garment. And what we're seeing here is actually a different execution of these leaves by the ancient artist. This is an intentional accenting of the leaves over the pink purple garment. And probably any of the luminescence we're seeing over the white tunic is actually coming from the tunic below. So I just want to wrap up and say I have a lot of more examples, but I think these really show that if we want to start tackling a lot of artworks on the macro scale more rapidly, we can really help ourselves by using the actual photoluminescence signature and the spectral profile to both identify and map it in more works of art.
Okay. Thank you very much to Roxanne Radpour, and now we're closing our meeting. Thank you.
My first idea was to make a very short comment. It's late, it's time to go for dinner. Then I changed my mind because I said they were suffering listening to 24 speakers. I am quite sure that they will be disappointed not to suffer for other couple of minutes listening to comments. The first comment is to thank the organizing committee, Alfonsina Russo, Chiara Anselmi, Francesca Boldrighini, Marco Nicola, and especially Virginia Lapenta, who was present in all the preparatory phase of this conference, and today she had to listen, suffering, because we exchanged many comments at home. The second comment is that the Bluenet is a very interesting network with a lot of scientific competencies, as we have been listening today, but it's also a very interesting network of very interesting human personality. Somebody called the family. I don't want to change Bluenet in Blue Family, but they can in a way became later on synonymous. I will try to make another couple of comments because really it's too late, but we promise to send in a short time a newsletter collecting the proposal that emerged today. For instance, this morning, Rescigno, then an archaeologist, made some very interesting proposals, and also this afternoon, two young scientists, Selvaggio and Marco Nicola, made some other proposal. We are going to make some proposal. For instance, I think that we are growing, and we are very many, so one reasonable way to operate in the future is to subdivide in groups with different interests without losing the entire project, which is an important point of view. For instance, we can collect all the new papers appearing, new preprints, and try to create a database of scientific papers that can be read only by some password, only by a member of the network. So these are some of the proposals. And also, we had in the past the request by especially museums that they said we would like to make our measurements because by ourselves in a way, so we can prepare a protocol how to set up a sort of blue lab. And of course, the people who spoken in the second section, very chiari Comelli, I call VC2, can prepare this paper to spread out and then try to have a kind of protocol, simple protocol, in which the VIL, which is the key technology, but also XRF, visible spectroscopy, so to make a sort of small blue lab, not very expensive, very easy to be used. These are the proposals that I will say, but in the newspaper we can make some other proposal. Wait for your response and then try to define which could be the best way to operate in the future. I think that this is, I am firmly convinced that will be really a pity to lose what is good for this network. I think that there is a lot of potentiality, both from scientific and also from the human point of view, because I must say that it's not so easy to stay all the day listening to 24 speakers and eventually to foolish comment by somebody else. So I thank you, all of you, for attending in such a serious manner. Thank you. Now it's time to go back.